Good morning, everyone, and welcome to day 3 of Online Faculty Development Program on Advanced Process Control, sponsored by AICTE Training and Learning Academy, organized by Department of Electrical Engineering and Department of Chemical Engineering, National Institute of Technology, Calicut. Before we start the session, I'll be quickly going through the guidelines that will help in the smooth conduct of the session. By attending this webinar, you voluntarily agree to the terms and conditions set forth by the AICTE and the compliance of the academia or industry offering this lecture. No contents of this webinar may be copied, recorded, or reproduced in any manner without the written permission of the AICTE and the compliance of the academia or industry offering this lecture. Please mute your mic and turn off your camera at all times. Do not use the chat box for sending personal greetings. Use it only to post your doubts on the topic. Do not click present now during the session. If you have any technical issues, make sure your internet connectivity is stable and then wait for 1 to 2 minutes. If the issue persists, use the WhatsApp group to address it. Our team will assist you. All participants must attend all the sessions and a test will be conducted at the end of the FDP. Those who get a minimum of 60% of marks in the test and an attendance of above 80% will get the participant certificate. Now I'd like to invite Dr. Kanakalakshmi ma'am to welcome Dr. Selva Ganesan sir. Ma'am, please. Hello, ma'am.
Good morning, everyone. I am very happy to introduce Dr. N. Selva Ganesan. So, Dr. N. Selva Ganesan completed his BE in Electrical and Electronics Engineering from MEPCO Engineering College, followed by ME in Control System from PSC College of Technology, and he completed his PhD from MIT campus on the topic of System Identification and Adaptive Control in the year of 2005. He has worked in Weldtech Engineering College as a lecturer and training research associate in MIT campus and lecturer in Pondicherry Engineering College from 2001 to 2008. He then joined as an assistant professor in Department of Avionics, IAST, in 2008, worked as associate professor and head of the department from 2013 to 2019, and is currently working as professor in IAST. His research area includes system identification and adaptive control, fractional order control, and fault detection and diagnosis. He has been a part of the project of modeling and controller development for micro actuator funded by ISRO, Chessboard, a chess playing robot funded by DSTE, and is currently working on design and development of brushless DC motor funded by ISRO. So we are very happy to welcome and invite you for this session. Thank you, sir.
Thank you, ma'am. Thank you for your introduction. Yeah, before start with the presentation, I would like to thank the organizer for giving this opportunity to present some idea about the design of PLC controller. Now I can share my screen. Okay.
Yes, sir.
Can you please allow? Yeah, yes, yeah. Now I can.
Sir, video also you can switch on, sir.
Okay, no problem. Can you able to see the slide?
Yes, sir.
Yeah. So here, the title of presentation today is Design Methods for PID Controls. So we are talking about in PID control, we are talking about PI, PD, or the combination of the all controllers, PID controllers, right? So let us go to the feedback system first. So normally we talk about open loop system, right? So open loop system have certain disadvantage, right? Suppose if there is a disturbance or if there is a uncertainty, maybe in the parameters. So what happens is there is a change in output. So with respect to the given input, there is a change in output. So that in output is desirable, then there is no problem. If the output is non-desirable, then we need to manipulate this input, right? That is what we want to go with. We would like to go with a controller. So what we do now, so let us take a simple example. Okay, we'll take an example. Let us take an example, simple tank process, right? There is an inlet and there will be outlet here, right? So what will happen now? Our interest is, maybe I can say Qi is the input and the Q0 is the output. Our interest is to maintain the level of the liquid in the tank, right? So I would like to say the height of the liquid, the tank is H. So what we normally do now? We normally write the relationship between input and output. So what is the output control variable here? Output control variable is H. Input control variable is Q. So what we do now? So normally we write the expression something like height divided by the inlet flow rate, actually Qi. So we will get the equation something like K by towers plus 1. Simple first order dynamics we get that, right? This is under the assumption that the system is linear and invariant model. That means the parameters of the model K and tau are constant. So hope in the previous lectures you learned about how to model it, how to identify the plans, how to design a controllers, various type of controllers also. Here we are talking about something related to that, but we'll see how the controllers in general be tuned actually with respect to the given process. So to start with, we are talking about the plant. The plant is something like a simple tank process, and the dynamics of the process, we are representing it as K by towers plus 1. We know what is the gain K, right? It is basically open loop gain, and the tau is the time constant. It basically decides speed of response. Okay, so normally the time constant is small in case of standard dynamics, so the speed is high, it's large. Speed is very high speed. So suppose if the time constant is very large, definitely that introduces sluggishness in the processor. It will slow down the processor. Okay, now what we would like to say here. So here this is the plant here, open loop plant. Now there is a possibility of changing parameters K and tau, right? So what we do now normally by changing the parameters K and tau, it will change the dynamics. It will change the dynamics. Means suppose the dynamics is something like, it's a first order dynamics. Dynamics is something like this form. Say for example, I have a system whose dynamics is something like this form, right? Suppose if the dynamic, because of some parameters uncertainty, maybe say for example due to disturbances, so I am suddenly pouring water here. I am introducing a disturbance here. So due to the disturbance, what will happen now? So there is a change in dynamics. So the change in dynamics maybe should not change the further processes. Say for example, I am introducing at t equal to t1. You say for example here t scale in x-axis, and by introducing disturbance here, what will happen now? There is a change, and finally it settles, something like that. So this changes can be a desirable quantity or maybe undesirable quantity. This is basically with respect to the next process. All right. Suppose connecting with another tank, or maybe another this output can send to the another tank for some other process, maybe stirring process or etc. So we need to know, we need to see that whether this dynamics characteristic is unwanted to the second level processor or not. Suppose if there is an impact, if this impacts maybe a second process due to the chain reaction. So what we supposed to do? It is supposed to be controlled. When there is a disturbance or maybe there is a parameter variation, so this has to be controlled. That is why people used to do with some kind of compensator. So we are keeping some compensator such that I can bring back to the original position, maybe in the faster rate and with a desirable margins. What do you mean by desirable margins here? Say for example, suppose in case of time domain, right? We are talking about two different domain of analysis of controllers. One is time domain. In case of time domain, normally we talk about rise time, right? In the one, and peak overshoot and settling time. right? And steady state error. These are the three parameters, four parameters, sorry. Normally we look into that. So we would like to control the rise time, peak overshoot also should be minimum, and setting time should be faster, and steady state error should be either should be minimum or should be eliminated in some cases. So this is in case of time domain. In case of frequency domain, we can also see the parameters like maybe a bandwidth, we can say the gain margin and the gain phase margin, or later frequencies like gain frequencies and phase frequencies, and so on. So depending on the requirement, suppose if you say I'm talking about in time domain design, suppose if my characteristics, this is characteristic is not desirable, this characteristic is not desirable. For an example, suppose what we supposed to do, I supposed to do some kind of compensator such that I can eliminate this. Say for example, instead of going like this, after changes, it will be like this. So there is no much change. So this can be a desirable quantity. Maybe less overshoot and maybe faster rise time, but less overshoot and less setting time and no steady state error or something like that. So these characteristics that we can reproduce actually with the help of some kind of compensation. We call it as in control system design as controller. So you studied different compensators like lead compensator, lag compensator, and so on. So in other form, we call it as PI controller, PD controller, etc. Okay, or the combination of PID controllers. So finally, what is our objective in the closed loop system is to maintain that desired specifications. So I'm giving a specifications, and my closed loop system should follow that specifications. So what we supposed to do? I supposed to design a compensator such that I can able to meet the desired specification. This is what our objective is. So how this objective can be enhanced? So we need to design a controller with certain procedure. So you learn many procedures. We are going to see few procedures, how the controllers are developed or designed actually for the given processor.
Okay. Sir, excuse me, sir.
Yes.
Can I interrupt you for a second? Sir,
yes.
Can you please switch on the video?
1 minute. Okay. I hope you can able to see my video, right?
Yes, sir. Thank you, sir.
Okay,
Thank you.
All right. So, the objective of this whole process exercise is to design some kind of compensator or controller, right, such that I can able to meet the desired specifications. So my close to specifications, as I told you, it can be a rise time, overshoot, setting time, and steady state error in case of time domain analysis. So finally, I have to see after design of controller, I have to see in simulation whether the required specifications, close to specifications are met. Suppose if it doesn't matter, we need to retune the controllers. We need to redesign the controllers, right? So normally we will say that these plants or the controller design, whatever the control system design we do actually for a given plant is workable for 10 to 15% of the uncertainties. Suppose if the uncertainties are within the limits, within this band, 10 to 15%, definitely your closed loop control systems will work. Suppose if you say that my parameters are varying and it is no longer well within the band of 10 to 15%. So maybe you can have other controllers, something like robust control systems, RCS. It is workable for a maximum of maybe I would like to say 30 to 40% band. I'm talking about uncertainties associated with the plant parameters. Suppose if we say that my value of k equal to 1 and tau equal to 0.0 and tau equal to 2, say for example. So the 10 to 15% means this is plus or minus 10 to 15%. That's what I'm saying. So you are unique. When you talk about robust control system design, it is workable actually for with the uncertainty band of 30 to 40%. Suppose the parameters keeps on varying and with respect to time t, then definitely your fixed control systems won't work. Right. So we need to have a adaptive control system. So this is there is no limit actually with respect to the plant parameters. So your plant parameters k and tau are varying, right? Continuously varying, right? So it means your controller also should be updated, right? So we are not going to talk about adaptive control systems, robust control system. Here we are going to talk about simple control system design for the given processor. Okay, so let us go to the details about how the control system designs can be developed. To start with the control system design, we would like to start with the structures. What are the structures to be defined of? So we normally define PID structure, right? So we used to have a P controller, proportional controller, and combination of proportional plus integral controller and proportional plus derivative controller and combination of these three parameters: proportional controller, integral controller, and derivative controller. The structure is defined as like this. So your C of S is nothing but Kp, right? All multiply with, normally we multiply it with E of S. Because if you look at the previous structure, right? So there is a controller sitting here, the input of the controller is error. It means that error signal is coming from R minus Y, right? Reference minus, actually we call it as actual desired value. This is my original value. So desired minus original provides you the error signal, and this error signal provides you, based on the error signal, your controller takes appropriate action. That is U of t is nothing but in process we call as a manipulating variable. Okay. So this is nothing. So like that, we can define the process definition of controller structures as Kp times Fs. This times Fs, you can say like this. So this is my structure Cfs, and maybe since it is input is Efs, so your output Cfs, right? Your output, this is my Cfs I'm talking about here. Your output Ufs can be written as like this. So I would like to say my Ufs is nothing but Cfs times Efs. This is what my, like that we can write the expression for remaining controllers. So, but we should be careful in defining the controllers, right? So some cases we define the controller. Suppose I have defined the control structure, which is something like Kp times 1 plus K by S. Sometimes we can write Kp plus K by S. Sometimes we can write the controller with the integral time constants and derivative time constants. So there are many ways of writing it. But finally, you have to follow some structures. Here, for this presentation, this design process is concerned, I'm using the structure, which is something like Kp times 1 plus K by S and Kp times 1 plus Kd times S in case of PD controller. And PID controller, I'm using Kp times 1 plus K by S plus Kd times S. This is a structure I'm using it for through the presentation. So where I need to tune the controller parameters Kp, Ki, and K. So these are the three parameters I need to do. So this is basically a 3 degree of freedom controller. So we can use 2 degree of freedom controllers like PA or PD. We can use single degree of freedom controller like a just simple P controller also. Okay. So we would like to know first of how to select these parameters Kp, Ki, Kd, because we define the structure now for the given control system. We define the structure, but we would like to know how these control system, how these parameters can be selected. If you look at this table, just I have represented the table. This table shows that with respect to the increasing value of Kp, how different performance indices, time domain performance indices are affected. So we say that, like I told you, in case of time domain analysis, we used to have a rise time, overshoot, setting time, steady state error, and we also talk about stability also in some cases. So with respect to the parameter Kp, if you look at this, rise time decreases. So this is decreasing and overshooting because of decrease in rise time. Normally, what will happen is my Kp is increasing, right? By increasing Kp, normally introduces overshoot more. Because of decrease in rise time. Decrease in rise time definitely shoots that overshoots should be more. But setting time, there is no much change, small change may be there, and steady state error is decreasing, but it is not eliminated. But because of the increase in Kp, right? Because of increase in Kp, it actually degrades the stability process. Stability is getting degraded. If you look at the parameter Ki, integral controller, right? What will happen is because of Ki, this decreases rise time. So ultimately, like Ki, Kp, it increases the overshoot, and setting time will increase large extent because of overshoot increases much. However, the biggest advantage is of Ki is eliminate the steady state error. It means that suppose if you say that I have a system, something like this, and where I'm applying a step input. Okay, so assume to be it's a second order dynamics. It oscillates. Suppose if it settles at the steady state value, maybe say for example, my reference value is 1. If it settles at steady state value, it means there is no difference between the reference value and the settled value. Maybe then we term as eliminated, 0, right? So that is with respect to the previous slides, we would like to say that my error will be 0. This is what I'm saying. If its error is 0, that indicates that your steady state error is eliminated. This is achievable only in case of integral controller, right? Ki. But the beauty of Kp is it will reduce the rise time, right? It will reduce the rise time. Rise time is reducing, right? Decreasing the rise time, I would like to say. So this is the beauty of that. Ki eliminates this, decreases. Okay, when you look at the Kd, what will happen here? Kd, there is no much change actually in rise time by introducing Kd, and it will decrease the overshoot. The strength is by decreasing overshoot. What will happen now? Definitely, the setting time will decrease, right? So setting time will decrease, but steady state error is concerned, there is no much effect there. But it can improve, stability can improve if Kd is very small normally. That's why if you look at the structure, or if you find that after design, if you look at the parameters of the Kp, Kd, normally you look at the Kd value, the value, numerical value of Kd, it's very small. That indicates that the stability is improved drastically. Okay, so by having a Ki, increase in Ki, normally we see that more overshoot, and it takes long time to settle. So these are the characteristics of the controllers which we are talking about. So now we would like to see how to use that table. So I would like to say that the first step is to determine what are the characteristics need to be improved. That is our first idea, first step. And once it is done, suppose if you say that my open system is working fine, there is no problem at all, right? So we don't go with any control system designs. Suppose if we say that my open system characteristics deviates with respect to its certain conditions, like maybe input disturbance condition or output disturbance condition and so on. So definitely what you do now, we need to go with some kind of controller or compensator such that I can able to meet the specifications. So here in this case, we talk about 3 parameter controllers, 3 degree of freedom controllers. One is Kp, Ki, Kd. As I discussed already, Kp actually decreases the rise time, and Ki eliminates the steady state error, and Kd decreases the overshoot and the setting time here. So I hope I can understand that understand from the characteristics of the controller parameters with the table. So this presentation is concerned, just we are talking about 2 different type of design, right? One is time domain design, and the second one is frequency domain design. I'm going to showcase how the time domain, some aspect of time domain specifications, time domain designs with respect to the given specifications. So if you look at the process industries, they widely use PIPD controllers, right? So with the specific requirements. So if you see that what are the different methods which are used actually are available or well familiar about by you yourself is Ziegler-Nichols method. So it's a widely used method because if you look at the literature, there are more than 100 tuning methods are available actually with respect to various class of plants. So these are all modifications of the Ziegler-Nichols methods, which was invented during the time of 1942. So there are another methods too, maybe one method, another method which can be widely used by the process engineers, and Chin-Horn's Rissvik is another method, and Wang Zheng Chen. These are the few methods just I have listed out for how these methods are used for tuning the controllers in the industrial process industries. Okay, so here we are not going to talk about all the methods because we have time is limited. So just I'm going to use a few methods to explain, maybe to make you understand how the controllers are designed or developed. So the first method we talk about is Ziegler-Nichols method. Okay, so Ziegler-Nichols method actually, it was, as I already told you, it was developed during the time of 1942, and this is basically to ensure the quarter decay response. What do you mean by quarter decay response? It means if you say for example, I have a system, right, whose response is like this. It goes like this, right? So suppose assume it is oscillating response, and my response is like this. Okay. All right. So what do you mean by this QDR method? QDR method says that the ratio of second to first overshoot. What is the ratio of second first? Say for example, I would like to say this is my first overshoot is A, and second overshoot is, say for example, B. So we are saying that B to A, the ratio between B to A should be 1/4. So you might be heard that 1 by 4th decay ratio. Actually, this is what the same thing only we are talking about, 1 by 4th decay ratio. So we call it as water decay response. So with respect to this, the ratio between the second overshoot to first overshoot, right? So that is maintained as 1 by 4. Like that, we can say C, D, F, and etc. So normally they maintain the ratio between D to A, the C, D to C, and so on. So that kind of design method we termed as that ensures that designs ensures actually this water decay response method. This Ziegler-Nichols method is mainly designed to maintain the QDR actually. Maybe with respect to second overshoot to first overshoot as 1 by 4, right? Magnitude. So the tuning formula here, if you look at the tuning formula, the plant given they have to consider as first order plus daytime model. Because if you look at the scenario, right, we in control theory in practice, normally we studied in our classroom first order model, second order dynamics, right? So first order dynamics and second order dynamics just by giving a step input or impulse input or maybe a different standard inputs, how the process can be or system can be analyzed. So because our work is very limited to that. Suppose if you consider for third order dynamics or higher order dynamics, it is complex to design. Still we can design, but it is complex to use solve with paper and pen, right? So this is one way of looking at the problem, and another way of looking at the problem is if you look at the process industries, it works with a 100th order of system or 50th order systems and so on. So making such models is a huge, and we need to find the way of solving such higher order dynamics. So such higher order dynamics normally reflect the behavior of FOPDT. Okay, that is why our control system design, when Ziegler-Nichols talk about that, they talk about, they consider plant as first order with daytime models. So it is something that looks like this. This is actually kind of representation for the higher order dynamics as well. Okay, or you can say, and if you say that no, I don't want to use FOPDT model, I want to use a second order dynamics. Yes, we can use that. The higher order system can be reduced because there are many methods for reducing higher order systems to lower order systems and apply and design of, for the design of controllers. That is also possible. So one simple method is using dominant pool methods. So the method of, suppose if we say, for example, I have a system whose dynamics is of 10th order, 10 pools are there assumed. So out of which the pool which is dominating, that can be considered, and we can make a model as a second order dynamics. This is something like close approximately closed models. Based on the approximated models, one can able to tune the controllers. So here this Ziegler-Nichols is concerned. He is talking about first order plant with data. So he's assumed to be how higher order system can be represented with the help of first order dynamics with data. So here k by tau plus 1, we already seen this, right? This is what we see, and he is introducing data. So e power minus ns. Okay. So can be represented in a general sense, we write it as tau plus 1 times e power minus theta s, something like that. So here the parameters we are using it as L. L is nothing but this, and your tau is nothing but T here. Okay. So using Ziegler-Nichols method, we have two methods actually. One is process reaction curve method, and second one is Ziegler-Nichols sustained oscillation method, right? So in the process reaction curve method, what we do now, we'd like to see given input. So I have system, and you open the controller now, and you inject the input, step input, you inject the step input here, and you get the step output, right? The closed loop plant, your controller is open now. This is controller is now open, and we are injecting the input, step input is injected, and you are getting the output, step output, and we would like to see that whether the curve is S-shaped. Right? If the curve is S-shaped, then you can apply this reaction curve method. So here we find the parameters. So say, for example, what you do now is we first step is just to draw the tangent line, all right, at inflection point. So this is my inflection point here. I can draw the tangent line, all right. So which cuts the steady state value k, and this point is nothing but in the time scale we call it cuts the time scale is nothing but t, that is nothing but time constant. Okay, so the remaining band, this band is nothing but your theta, or nothing but, or maybe here we are saying that L. So we know the information, steady state information is k, and the time constant information is t. and the deadband information we also know from the response, the experimental response is L. And based on this information, one can able to find the respective parameters. For example, suppose I want to find the parameter, only just I'm using a P controller. So the P controller can be obtained by Kp, that is the constant can be obtained by 1 by A, where A is nothing but K multiplied L divided by T. So these informations are available from the experimental example. Like that, one can able to find the remaining parameters in case of PI or in case of PID controllers. So it is something like a lookup table type is given, and after the experimentation is conducted, you can just observe those parameters K, T, and L, and you substitute those values here and to get the final parameters. He proved that this controller settings provides you this 1/4 decay ratio. Okay, finally. Let us showcase what we have done actually from the Ziegler-Nichols method 1, that is reaction curve method. So I'm assuming the value of K is 0.2941 and L is 0.76 and the time constant is 1.96. So what they did, suppose in case of P controller, so this is my P controller here. My P controller provides will be computed based on 1 by A. My A is nothing but K by L times T. So using this formula, I can able to find what is my P. So this is my proportional controller Kp. Like that, I can able to find in case of PI controller Kp times this is Ki. I can able to find those parameters based on the formula which is given. So it is something like a lookup table. So just if you by conducting experiment, you can observe those parameters, and based on the parameters, one can able to find what is my parameter, what is my controller parameters are. So you based on the structures which we selected. So there are 3 structures which is selected defined here. One is P structure, and then Pi and PID. On the other hand, you have a Ziegler-Nichols sustained methods, right? Sustained method of oscillation. We call this Ziegler sustained method of oscillation. Normally, what we do now, I have a closed-loop system, and I normally keep controller K. So just I would like to try. Maybe I have plant here. My plant is Jocas, and my controller is here. I'm keeping only gain here, right? So with the help of gain, right, I can adjust the gain. I can start the gain, I can increase the gain, and to make the system to provide sustained oscillations. It means by increasing the gain, after some times, what will happen now? In case of root focus, for example, suppose there are some poles and some poles are here, right? And by increasing the value of K, so it moves to the left hand side of this plane. And just I'm considering the case where the poles are moving to the left hand side of this, right hand side of this plane for certain value of gain K. That gain we normally call as critical gain, and the frequency we call as critical frequency, right? So in the response, if you say in the system, in the closed loop system, what do you see here? By increasing the value of gain K, you can allow the system to oscillate, right? So under this condition, say for example, the value of K at critical. So what will happen now? Your system start oscillating, right? That provides you sustained oscillation. So instead of having like this, it provides you sustained oscillation, something like this, since the poles are lying on the imaginary axis, the omega axis. Okay. Right. So this gain, based on the gain and frequency, one can able to find the parameters. Say for example here, so critical gain is Kc here, and he has defined a tabular column like what we seen in the previous method, so method 1. So I can able to find 0.5 times Kc becomes Kp, and 0.4 times Kc and 0.8 times Tc becomes Pi controller, Kp and Ki, and for parameters to come with the parameters of Kp and Ki. And in case of PID, we are defining 0.46 times Kc, 0.5 times Tc, and 0.1 times 2 times Tc, where Tc is nothing but 2 pi by omega c. So if you know the information of critical gain and the ultimate frequency, one can able to find the parameters of the controller using this table. So this is also some kind of lookup table only. But you might ask, is it provides the optimal solution or not? Definitely, some cases may provide, some cases may not provide. So we need to do with some further tuning. So initial values of those parameters for the given plant can be obtained with the help of this. And later, if you are not satisfied with the given characteristics, one can able to fine tune with the help of other methods. Okay, so we are not going for that, and we are going to explain how these parameters are tuned actually. Okay, let us on the other hand, we talk about the prospective equations. How to find the value of Kp analytically. So this is where I'm considering as a simple P controller design. right? I'm assuming I have taken a servo systems, right? Simple motor control systems where the dynamics of the motor can be represented by Km divided by S times tau m S plus 1, where Km is the feedback motor gain, right? And Tm is the mechanical time constant. Here, the electrical time constant is neglected. Normally, the provide it comes like something like this form: tau Es plus 1 and tau ms plus 1. This is the motor control, simple armature control, speed control of machine that provides you the dynamics, which is something like this form, right? Y2V. But this is nothing but theta with respect to the voltage applied to the armature, right? VA. This is my dynamics. Normally the electrical time constant is very small compared to mechanical time constant. Under this condition, the servo systems we defined finally as a simple second order dynamics. So we are reducing into Km divided by S times tau m S plus 1. Since mechanical time constant is little large compared to electrical time constant, we are neglecting it actually. So we have only second order dynamics, right? Suppose if we say that I want to design a controller. So for example, P controller, I have defined here as P controller, right? I want to design a P controller. How to do that? So you have here, so this is my G and this is my GC. So what do you do now? I want to find the relation between Y to R, right? What is my Y to R? Y to R is nothing but GC divided by 1 plus GGC under the assumption that the feedback gain is 1, right? So we are doing the same thing here. I'm finding the closed loop transfer function. So Kp Km divided by Tm divided by S square plus S by Tm plus Kp Km by Tm, right? I hope anyone can able to follow this. This is GC divided by 1 plus GGC. So just we are doing this here. I have obtained the closed loop dynamics as Y2. So Y2R. Okay, this is my closed loop transfer function of the system. So what do you do now? I want to find the gain Kp, right? This is not known actually. So Kp is known to us. So the Kp is known, Tm is known, right? Kp, Tm and Km also known to us. Only say Km and Tm is known to us. Only Kp is not known to you. So Kp is not known. This is what we want to find actually. So how to find it? Find this Kp value here. So I can compare the standard second order dynamics because we study our bread and butter is second order dynamics because we always equate it with a system whose dynamics is second order, right? So my second order dynamics represent as omega n square divided by s square plus 2 zeta omega n plus omega n square, right? So I can equate directly this equation and this. So maybe say for example, this is my equation 1 and this is my equation 2. By comparing equation 1 and 2, so what will happen now? I can able to find what is my parameter omega n and zeta. So omega n can be written as square root of this and 2 zeta omega n is 1 by Tm. So this equation, by solving this equation, right? Finally, what you get the value of Kp, right? The unknown controller parameter Kp, which is something like 1 by 4 times zeta square Km and Tm. So what all are known to you? M is known, Km is known. Zeta is also known because we are defining this structure. Say for example, I am defining my zeta value is supposed to be, say for example, 0.6. So my omega n is supposed to be some 1 radians per second, sir. For example, I'm saying something like that. So based on this specification, I can able to define this second order dynamics. In the sense, this is what I wanted as the output, right? So that's what the meaning is. So simply we are comparing second order dynamics means I have my system should provide the response with zeta equal to 0.6 and omega n equal to 1 radians per second. So under that condition, we are comparing with second order dynamics and we are finding the value of Kp, which is something like 1 by 4 times zeta square Km times Tm. Okay. Let us understand what we learned actually. So with the help of a simple simulation, right? I'm assuming Km equal to 1, Tm equal to 0.5, and overshoot is 4.6. Okay. So which leads to the zeta value of 0.7. So this 0.7 indicates what actually your peak overshoot. Maybe you can say that 4.6 here you can substitute 4.6 as here. And so that I can able to find what is my zeta is. So these formulas and all, well, you are learned already. So I'm not going to the history behind that. So with the help of these specifications, KP is available, TM is available, peak overshoot I am defined as 4.6. So what the 4.6 equivalent zeta is computed as 0.7 with the help of this formula E4 minus pi, pi zeta divided by 1 square root of 1 minus zeta square times 100. We normally we write in terms of percentage. So by using this, what will happen now? These parameters are known to you. And if you look at this, what do you need? Zeta is required, Km is required, Tm is required. Just by substituting, simple substitutions. By substituting the values K, T, and zeta, I can able to find my Kp. So I obtained the value of Kp, which is something like 1.0204, right? So now I am substituting here in the feedback systems. So I am just, this was replaced with that value, right? So the value Kp is replaced now. Now, then we applied the simulations. So after simulations, what you learn here, this is a simulation, course of simulations with respect to the given step input command. So the magnitude of the step input is given as 1, right? Unit step input is given. So we are looking for how the response is. So whether the response is meeting the given specifications or not. Now the specification is what overshoot is 4.6, right? That is what is given here. So we would like to see here after simulation, if you see this overshoot, I hope all of you can able to see that I have placed that point here. So if you look at this now, exactly the overshoot is 4.6. So what is there is no ambiguity actually. The point I'm saying here is when you look at the analytical models, right? The specification to be met is here for the given closed loop specification to be met as it is overshoot, right? Only overshoot is given. So one degree of freedom controller is sufficient actually to maintain the overshoot, which is of 4.6%. So so after doing this, the analytical expression, I found that parameter Kp and substituted the parameter Kp in the simulation. I found that it is reaching exactly 4.6, right? We are not other parameters are not our control because we are not adding as a specification for the design of Kp controller because it is basically single degree of freedom controller. So 1 degree, right? 1D is only Kp. 2 degree of freedom either Kp, Ki or Kp, Kd. Okay. So 3 degree of freedom control, you say that Kp, Ki, Kd. Three parameters. We are talking about single parameter controller. So single parameter controller, I can able to meet only one solution because number of it is basically mathematically speaking one equation, one unknown, right? So it provides you a unique solution. That's what from the response we observed that it is exactly meeting the specifications which is given given to the closed loop simulation. That is of 4.6% of overshoot. Suppose when you want to design other controllers, same way we can develop other controllers too. So I suppose I have considered for another example just to make it understand the analytical way of deriving the controller. So PD controller, just consider PD controller, right? I'm using the same thing here. So structure is given as PD. So KD, KP times 1 plus KD times S. This is considered here, and you make the closed loop dynamics. That is Y of S to R of S. You find, and that equate with the standard second order equation, right? So you can able to find the parameters of the KP and the parameters of the KD. So both the parameters you can able to find actually with the help of simple analytical expression. Okay. So, so what is given here? Actually, we are talking about.
ಇಲ್ಲ ಅವ್ರದ್ದು ರೆಡಿ ಮಾಡ್ತಾ ಇರೋದು ಈಗ ಬಿಜಾರ್ದೇನೆ ಹೋಗಿಲ್ಲ ಮಾಡ್ಕೊಂಡ್ರು ಮಾಡ್ಕೊಳ್ಳಿ ಹೋಗಿ ನಾವೇನ್ ಮಾಡಕ್ಕಾಗತ್ತೆ ಲ್ಯಾಬ್ ಎಕ್ಸಾಮ್ ಅಂತ ನೆನ್ನೆನೆ ಹೇಳಿದೀನಿ.
Can the participants please mute their mics?
Fine. So here, what we are talking about is for the given specification. So the given specification, like same specification was given. Overshoot was given as a specification, and in addition to the overshoot, we are also giving a setting time because it is basically 2 degree of freedom controller. So the 2 degree of freedom controller, I can be able to have maybe more maximum 2 specifications. So in the 2 specifications, in addition to overshoot, in the previous case, we are providing setting time as well. So based on this information, one can able to find the equation analytical expression, which is Kp equal to this and Ki equal to this. So if you know the parameters omega and Tm, Km and zeta, I can able to find what is my Kp and Kd. So it is basically that provides a unique solution. I am not giving a example here. So because it is a by you can assume some values and get those parameters Kp and Ki and just substitute that into the simulation. You can able to get what you have seen actually from the first case. Okay. So to reduce the time, I have not included that. On the other hand, people are talking about time domain designs. People are talking about minimization or minimizing the performance index. So this is under optimization methods. So we are not going to talk about, and here we talk about two different kind of optimization. One is constrained optimization, and second one is unconstrained optimization. So most of the time we do with unconstrained optimization, and this is basically with respect to the given performance index, like what I'm showing here. Integral absolute error, integral square error, and integral time absolute error. So each error have its own specifications. So integral error have certain specifications, integral time absolute error have certain specifications, integral time absolute error have certain specifications. So we would like to see that what kind of characteristics normally we need to have, whether you want to have a good transient characteristics or you want to have a good steady state behavior. So depending on the characteristics which you are selected, one can able to choose the performance index. Suppose I have a system whose transient behavior need to be controlled to Pakka. So what normally we do is normally I use integral square error because it gives a small error is magnified. So under that condition, you get a controller which is very sharp, actually, very good transient behavior. You want to control steady state behavior, normally we use this IAE and ITE controllers. Normally, when you talk about control system design using optimization methods and etc., normally there is a trade-off actually between transient behavior and steady state behavior. You want to choose the performance index carefully, such that one can be able to meet their required specifications, possibly transient specification, tight transient specifications, or sometimes tight steady state specifications. So always have certain trade-off actually between suppressing the transient specification and steady state specification together. Okay. So these are the performance index normally we define as like this. Right. Now, like I told you, when to use this ISE and the IPE and IAE. So we normally will see if you have a large error, right? Large error normally contribute during the transient period only. Normally we use ISE, integral square error, than IAE, because IAE normally there is significant actually in case of a large error. It always provides good accuracy in case of lower errors. So that is why when you talk about during the transient period, normally we try to transient period, we normally error over error occur. So we use ISE for the controllers. Okay, minimizing the controllers. That is one aspect of looking at the problem. So and also this ISE at the same time I would like to say the ISE actually provides larger times setting time, so that increase the setting time. So that is because when you look at the error during the time of infinity, right, minimum, right, if the error is minimum, the minimum error, the square of error is what? Suppose if we say I have an error of 0.1 at steady state, so that square of error becomes 0.01. So it is least significant compared to integral absolute error. That is why during the period of to get the better transient behavior, use ISE. And better steady state behavior or better steady state profiles, we normally use integral absolute error minimization controllers. Okay, so the final minimization methods which we talk about ITE, that ITE is integral time absolute error. Have absolute error and just normally we are multiplying the time. So what is happening now is that we are giving some weightage actually. So we are giving more weightage actually to the errors such that it occurs later in time. It means near to steady state. So by multiplying, because when the plant is running, when you're talking about after some time, after transient behavior is over, you are talking about steady state, and by the time that the error will be time will be more, and this time will be multiplied with a small error which is occurring. So that actually clearly tells you that you have a very good accuracy, tight control actually in that steady state behavior in comparison to the transient behaviors. So this is the way actually one can choose the performance index actually based on the requirement. So we cannot choose simply minimizing ISE or IAE or ITE for the given process. We always look at the process behavior and see that what kind of behavior you need to control, and depending on the requirement, you decide whether you need to have a performance index something like ISE or IAE or ITE, or there are many more indexes actually which are used. Actually, even some cases we used for minimizing in our fraction designs and all, we used to have usability. This is another kind of performance index. So we can use minimum energy. So we call it as the energy minimum energy. Here we are talking about minimum error. And you can also talk about the performance index can be a minimum energy also we can talk about that. So these are the these are the ways we can define n number of performance indexes. But these are the whatever I am talking about actually this are the standard performance index which are used in many of the researchers actually for the tuning of controllers in using optimization methods. Okay. Right. When the moment you talk about how these controller parameters can be obtained by minimizing this, so we need to have optimization, right? So if you look at so normally we use simplex method and etc. There are many methods, no, DP programming and etc. So there are many more methods used for minimizing the controllers, minimizing problems. So here we are talking about, I am using a simple function which is used in, which is available in MATLAB. That is fmin search. Okay, so this is the function used. I have given the code also here, fmin search. There are two functions which are available. One is function to be minimum in the boundary, that is a search we are talking about. Another one is fmin con. So this is required only for constraint optimization. Suppose if we say that with respect for the given performance index, in addition to the performance index, I need to minimize certain things, right? So we have a certain constraints, can be equality constraint or inequality constraints, but after minimizing function have certain constraints. So with certain equality or inequality constraints, and we use fmin con, right? But here we are talking about fmin search because it's a very simple unconstrained optimization, because only we need to decrease the error or maybe usability or whatever. Okay, so we can use the function here, and we can run this function. This is basically work with the model of Nelder-made approach. This is the algorithm Nelder-made, NELDER. This algorithm is actually used for optimization. It is like you learn a decent gradient method and so on. No? So it is a Nelder-made method. So Nelder-made is a one optimization method which uses very good. It is basically a deterministic model, so not stochastic model, and to some extent it will work for stochastic. Okay. So if you want to, if the process is purely stochastic, we need to go for some kind of heuristic models for optimizing parameters, controller parameters. And we are not going to talk about the heuristic models here. We are talking about a very deterministic model, as we are assuming that the plant parameters are constant and how these controllers are tuned. So under this certain conditions, under certainty, I would like to say that this Nelder-made method is always better actually for finding the good, finding the controller parameters with good accuracy. Just we used simply running and running the program in search actually, and we got the parameters for the given plant. So for example, if the plant given here is, I used various controllers here. Here the structure I'm using is KP here, and this is KI, and the parallel structure I'm using for controller, and I'm using a fifth order dynamics I'm considering. Some can randomly I have selected here for just for to showcase you stimulation actually for today's presentation. And we have got, with respect to the minimum integral absolute error, I have got the controller parameters are this KPK, KD or like this. And with respect to ISE, integral square error, I have obtained the parameters, controller parameters from the fmin search is this. And the third one, with respect to the ITAE, right? I have obtained the control parameters, KPK, KD. So I'm using a simple PID structure, and I'm trying to find the parameters KPK, KD with respect to different performance indexes. So first performance index is IAE, and second performance index is ISE, and third performance index is ITAE. So I have obtained the response with respect to ISC as something like this, So if you look at this, it takes long time to settle. If you look at this problem, it still further takes time, right? So ISC normally introduces more settling time, actually, more settling time, and whereas this IAE normally have less settling time. So when you want to go with less settling time and some trade-off, actually that provides your information ITE normally provides some kind of trade-off between the transient behavior and steady-state behavior, but it is very well work for for controlling the steady-state conditions, steady-state characteristics. So this works. You see that it settles very faster, and overshoot also very limited. Actually, it is even less than 1.1. 1.1. Yes. What you're seeing here is approximately 1.1 here. And in case of ITE, you can able to see that it is well controlled. Like some extent, like this, I would like to say that this process it works well, and it doesn't mean that it works well for all process. Suppose I'm using complete certainty, everything is constant, so there is no variations actually introduced in the plant parameters or any disturbance conditions also not simulated actually with this. Just to showcase you, I have simulated this. I am using MATLAB and just showing you some response actually for your understanding. You have seen that other methods. Other methods are maybe graphical tools, like you see in root locus method, right? So one which is in S domain we use actually the design of controllers, and by placing the codes, controller codes, one can able to find the root locus such that I can say that whether my specifications are better. So this is another graphical tool actually for design of controllers. This we are not going to discuss it here, right? So let us move on to the frequency domain. So what we learned actually so far is we talk about time domain analysis and frequency domain analysis. In case of time domain analysis, we talk about analytical expression, how analytical expressions can be useful. But only point is the analytic for the design of controller using the analytical expressions. If that provides you a unique solution, that is an advantage. At the same time, the disadvantage is we are always trying to equate with the standard second order dynamics. So far to get the parameters. So this is one limitation section over here. And some cases, sometimes we say apple cannot be compared with the orange. Suppose the dynamics of your coastal dynamics is of fourth order, and how can you compare with second order dynamics? Yes, it is. It can be done only by reducing your final coastal dynamics of fourth order to second order, and then you compare with second order dynamics, which is defined. Okay, so. So this is one way we learn, and we also learned some kind of methods, which is a generic method like a Ziglar-Nichols tuning method 1 and method 2, like this reaction curve method, and we also learned the sustained oscillation technique methods for minimizing this. So we also learned something like minimizing the performance index like errors. Or we can also minimize U square also. So, or something like what I defined, what I told you as optimization method, some kind of unconstrained optimization method, one can able to apply and to get a control parameters. So these are the few methods which we learned actually, right? We use actually for the design of controllers. Here, on the other hand, we have a frequency domain. So in case of frequency domain, right? Frequency domain, normally we talk about the controller KD, right? Same controller we are talking about, but we would like to see that how many number of specifications to be met actually. So suppose if we say that I have a controller, the ID controller, so whose parameters are KD to meet the specifications which are phase margin and gain crossover frequency and robustness to gain variation. So we know that gain crossover frequency and phase margin, right? In a Bode plot, normally we conduct the test, right? Two tests will be conducted, and one is frequency domain test. So with respect for the omega, right? We give the input sinusoidal, and you get the output also sinusoidal. Under this condition, I can vary the frequency such that I can able to get the magnitude and the phase. So these two information I get with respect to different values of different input frequency, right? So this is under this condition, I can able to draw two plots in case of Bode plot. So magnitude versus frequency, this is one, and phase versus frequency, this is another. So I'm talking magnitude versus frequency here and phase versus frequency here. There are two plots actually. So we call this Bode plot or Fourier plot. We can combine these two things actually with the help of Nyquist also. So we are not talking about that here. We are talking about simple Bode plot here. So Bode plot contains two plots, magnitude plot and phase plot, and this magnitude plots is here, and from the magnitude plot, suppose if we say that I have magnitude plot something like this, right? So the magnitude crosses 0 dB line, right? This is my 0 dB line, right? That is indicate omega DC. So gain crossover frequency. That is what we are saying, that omega C. Here, gain crossover frequency. So I have a phase plot, right? So I have phase plot. We can say like this, something like this. So with respect to the phase, I can able to measure what is my with respect to the gain crossover frequency, I can able to measure what is my phase is. This is nothing but phase. So we are talking about frequency domain controlled system design, where the specifications are frequency domain specification like gain crossover frequency. So I have defined gain crossover frequency is gain crosses 0 dB line. That is your gain crossover frequency, and phase margin is here, right? This is my phase margin. So these two are known to us, right? Because we learned actually from the control theory, basic control theory, that gain margin, phase margin, gain crossover frequency, and phase crossover frequency. These are the 4 parameters we learned actually. And here for the design we are using gain crossover frequency and phase margin. So with respect to the gain crossover frequency, we measure the phase margin. So these two will be treated as specifications for the given control system design. Okay. So what is the third one? Because this is the 3 degree of controller we are using. That is KP, AI. 3 controllers, so we need to get the unique solutions. So when you get a unique solution, 3 specifications. Under this condition, I'm using a third specification as robustness to gain variations. Most of the fractional control designs, right? You learned, I think, in previous session, yesterday session, about how the fractional controllers can be developed or designed. So normally in the fractional designs, there are many specifications we choose. This is one of the specifications used for design purpose. So what this indicates? We call this iso damping. What do you mean by that? So it means, say for example, we are talking about Bode plot here, right? So I'm talking about only phase plot here. Okay. So my phase plot is like this here. So what is happening now? We are talking about robustness to the gain variation. So what do you mean by gain variation? Suppose for the given k, this is my given, my omega GC is crossing at this point, right? Suppose I'm changing the gain k, I'm increasing the gain k. What will happen now? By increasing gain k, your Bode plot is getting shifted up to. By decreasing gain k, it is getting shifted down, right? So either it will go up, either it will go up or it will go down, depending on the gain value. So suppose by increasing k, it will go up, by decreasing k, it will go down, right? So, so this is the point I'm saying. So increasing or decreasing, either it will your magnitude plot getting shifted and things like that. So by shifting this magnitude plot, what will happen? By shifting this magnitude, your gain will decrease. In case, suppose for example, it will change. There is a change by increasing or decreasing the value of gain k. Suppose in this plot is concerned, by increasing gain k, it is shifted here. So my phase margin is getting reduced. Suppose if you are increasing A, the phase margin is changing. Maybe high, or sometimes it will be a low, right? Depending on the response time, right? So what is happening? There is a change in response. There is a change in phase margin. But change in phase margin indicates what? Change in phase margin indicates in time domain, right? I'm saying I'm writing y with respect to t, right? So for the given omega, some value of k, my response is this. Okay. Suppose if you are increasing k, what will happen now? It overshoot will increase, right? So this is what is happening now. Overshoot will increase. So what I want now? So because of this phase margin, change in phase margin, decrease in phase margin, I would like to say, decrease in phase margin, there is an increase in overshoot in the time domain. Right? Finally, we all work for time domain only. Even though if you design a controller with frequency domain, finally we can able to see only time, right? So how the response is varying with respect to given time. So overshoot will increase. What we wanted now? We wanted to have a same overshoot. It means, what do you mean by that? It means, so I have system, it is like this. All right, by changing this, right, by changing the gain k, I should not get change in overshoot. Suppose, for example, I have like this. If you say, you look at this now for different values of k, right? I'm changing the value of k, but suppose I'm getting the same overshoot. But previously what I told, by changing the increasing gain k, it will decrease the phase. In turn, it will increase the overshoot. But what I wanted now, I would like to maintain the phase margin constant. So how to maintain the phase margin constant with respect to the given omega c, right? I'm differentiating this d phi by d omega at omega equal to omega c. So what will happen now? I can maintain, so I can make this area flat. The face area, I can make it flat. That is what I'm doing here. This can be flat, either it can go up or down, whatever. This area can be flat, so that increase or decrease, the omega, increase in omega GC or decrease in omega GC, it will not give any impact in changing the phase margin. Under this condition, what will happen now? My overshoot is maintained. Even though I have a different price time and things, but my overshoot is constant. This specification, these things can be achieved only by using the condition, isodynamic condition. So we call it as robust. This is called characteristics we termed as a robustness to gain variation. So that is nothing but isodynamic condition. So that is by keeping the slope, phase slope, which is constant equal to 0. When it is 0, by making 0, what will happen now? This is constant, right? So it means that irrespective of the value of gain k, that your phase, your magnitude may change, omega GC also may change, but your phase margin will not get altered. This actually ensures that my overshoot is constant actually throughout the process. Okay, these are the specifications, these specifications given, and this is available, these derivations are available. If you are not able to find from literature, I can circulate actually this derivation. So using this parameter, Kp, Ka, Kd, okay. Using this parameter Kp, Ka, Kd, one can able to find the corresponding controller parameters. Kp as here, Ki as maybe it is a little complex derived expressions, but at the end you get the solution of this unit. So if you by using this, Kp is here, and I have a Ki here, and the Kd is here. So finally, it become an equation, 3 equations for the given 3 unknowns. So what are the 3 unknowns which are taken? 3 unknowns, three specifications. Unknown means I'm talking about specifications. 3 specifications are phase margin, gain crossover frequency, and robustness towards the gain variation. These 3 are the specifications which are considered. Under this condition, we are not using any optimization method here, since number of specifications or number of parameters available in the controllers are equal, 3 numbers. So I am directly using way of solving the expressions analytically and finding the parameters Kp, Ki, Kd. So this is the way normally we obtain the parameters Kp, Ki, Kd. Okay. Okay, let us consider just to demonstrate the controller which we talk about frequency domain. We are using the T as this, and we are using L, that is dead band is 0.01 seconds, and the time constant is 0.4. And omega GC we are giving is 10, and phase margin is 50. This is what my closed loop specifications are, along with d phi by d omega at omega c. So 3 specifications, 3 unknowns. So by using the previous formula, the Kp, Ki, Kd, I can with the known parameters, I can able to find the parameters Kp as this 2.7425, and Ki is 25.7861, and Kd is minus 0.0500. So by substituting this, right, by substituting this controller, what will happen? Just you can draw the model. So I have a G here, I have a GC here, right? So I can able to draw a Bode plot, GGC, right? So my open loop Bode plot is this, and you can find the closed loop information whether it is meeting or not. But omega c given as 10 radians per second, and the phase margin is 5. So now you look at this, 10 radians per second is meeting, and look at the phase margin here. at omega c phase margin is 50. So omega c here, this is what I'm saying. So the magnitude crosses 0 dB line, that is gain crossover frequency omega c, which is 10 radians per second here. This corresponding phase is this. Phase margin is this. This is nothing but phase margin 50. So whatever the specification which I had given is meeting. And we also have certain another specification, something like d phi by d omega at omega c is equal to 0. So with respect to this, my phase should be flat. If you look at this now, if you look at this is flat. Hope all of you agree. So for the given region, region of K, so my specification omega is constant. Sorry, my phase margin is constant. That clearly indicates that my overshoot is constant with respect to the variation in K. Suppose if you say that I have a border plot, right? So my plot is varying something like this. It goes like this, and another plot varying like this. So what will happen now with respect to this? With respect to this, if you look at this, my phase is maintained constant. That phase maintained constant is that is due to this condition d phi by d omega omega c equal to 0. Because of this condition, it is. Suppose if this condition is not given, I can exactly can meter, but this flatness will not be there. Okay, that is a different. So hope all of you can able to understand and appreciate how these controllers normally designed for in frequency domain. We can also try with the gain margin and etc. Other specifications also we can use, but widely used specifications in closed loop dynamics and frequency domain is omega gain crossover frequency and phase margin and isotropic condition. So other conditions also we can use. Other conditions is something like we say that sensitivity. So sensitivity condition and complementary sensitivity, etc. There are other conditions. We can use sensitivity condition. We can use complementary sensitivity conditions, and other conditions which you like. We can use it for the design of controller. But here I'm restricting only with respect to three conditions to make it understand. But the only problem by increasing the more number of conditions, so the solution is not unique actually. So we need to apply a optimization method for doing that. That is one aspect of looking at the problem, or you can use higher order controllers. So that is always perfect. Okay. So here I'm not going to talk about those control system designs here. Okay, and let us quickly see how this control system design is performed. So for what we talked about, we are talking about the controller planned, and we are talking about the controller for the given specifications omega d, omega ec, and phase margin and isotropic condition. With respect to that, we are seeing that how whether that closed loop design can able to meet the same specification or not. So it met. So we learned that. Now we will go with some general specifications. How that the control system design can be developed in frequency domain with some general specifications. So here we look at this now. So for an example, we are saying one can design two parameter control. Say for example, I want to design PD controller to meet the specification. Say for example, phase margin and you can analytically derive the formula for selecting the structure. That is what normally we do. Suppose if you have two specifications, I want to develop a PI controller, I can able to do it. Suppose I have three specifications, I have three different controller like PID, I can able to meet the specification with an alpha analytical structure. Okay. Now we'd like to understand how these frequency domain characteristics are getting altered with respect to the given design. Okay, let us see first proportional controller now, and we'd like to see three things. One is proportional, and second one is PI, proportional plus integral, and third one is PD controller. So the first case is a proportional controller. So what we do now by using a proportional controller, that only gain is added, right? Simply gain is added. So it is something like take k by tau plus 1. This is the process. This process multiplied with simple gain. So gain is multiplied. So what will happen now? Gain multiply gain. What will happen now? Is like I told you that magnitude plot either can go up or down. That's what it. But however, there is no effect on the phase. Like I told you, there are two plots which we talk about in frequency domain: magnitude plot and phase plot. So by adding a gain, so what will happen now? Either it will shift upward direction or it will shift downward direction in the magnitude response. So however, phase response there is no effect actually. So because it is independent. The phase is independent of this magnitude. So there is no effect on the phase. So what do you do now? The ability of the gain now, you can say that to change the magnitude only, but have no effect on phase. exploiting the design of controller is modified. This is what a conclusion is. This is with respect to simple P controller. So by adding a P controller P, by adding a controller PI. Suppose what you have to happen now, this controller indicates what actually KP. So you have PI controller, right? So it is adding again KP. This is what we are saying. KP is added here. So what is happening? The first order lead. You have a S plus KI. So it's there is a 0 and an integrator. So normally it looks like KP. Simply if you write KP plus KI plus something like that. Suppose we are adding a parallel structure, so we write KP plus KI plus. Right. So what will happen now? S times KP plus KI divided by S. So what is happening now here? So here, so this can be simplified as S plus KI by KP, something like this. So it is clearly indicates that some kind of code, right? I'm in the general sense we are writing S plus KI divided by S. This is what we are writing here. S plus Ki is here and from the S. So your PI structure normally comes with 1, 0 and 1 integrator. That is one pole at the origin. So what will happen by adding this and this? So what is happening now? This increase the system type. So type is increasing because of the integrator. It introduces a type here. Introducing type, what will happen? It eliminates the steady state error. That's all. Simple. So because of this integrator, right? Because of this integrator, it eliminates the steady state. It introduces type and hence it eliminates the steady state error. So that is normally why one use PA controller. Suppose when you want to have a system whose system comes with a system inherently having a steady state error, one can use PA controller such that you are able to eliminate the steady state error, or you can say that steady state error is 0, right? So this is what normally we do in case of PA controller. In case of PD controller, so PD controller is same way we are looking for. So PD controller KP plus KP times S. So it is something like this. So you say that KP, something like that. So we are writing some simple formulas, some simple formulas. A first order lead. So S plus 1 by K. It is only 1 0, right? Only 1 0 is that. There is no pole, right? So only 0 is available. This means what actually you have a PD controller, right? Raise the right hand end of the both magnitude and the phase part of the open loop system. I have a open loop characteristics and I'm introducing, I have G, I'm introducing the PD controller. So I have a G here, I'm introducing the PD controller, something like 1 1 0, right? We are multiplied with this G controller. So what will happen now? So it will be like this. The magnitude will go like this, right? It will increase, it will go in the right hand side because that provides you plus 20 dB by decay. So from this is my corner frequency. After that, plus 20 dB by decay. That's why we are saying that in the magnitude phase plot of the existing open loop system, both sides, the right hand side, right hand side ends actually it goes like this. This is in respect to magnitude. Your phase also will be like this. It will go to plus 90 degrees, right? So in case of G pole, it goes to minus. That is what will happen actually in this case, in case of PD controller. What will happen when you are combining this? So the combining these two, right? So it has what actually 2 zeros. Like I said, as the previous case, S plus Ki. So I like to say S plus Ki by S. This is the Pi. Then S plus. We say the 1 by Kd is given, right? We say 1 by something. So it means I have 2 zeros. This is my first 0 and this is my second 0. And I have one pole which is attached. So that is integrated, right? That is what that we are defining. Suppose if you look at this here, if zeros are here, right? The control is actually a combination of Pi and PD. Whatever we learn here, this structure is multiplied with this is nothing but a simple PID controller. When we talk about the zeros are here. Okay. So what will happen now? The pole at the origin here, right? So that pole at the origin, what will happen? It will increase the type by 1 and hence it eliminates the steady state error. That is what it does actually in PID controller. And second point is the 0 is added to stabilize the system, right? 0 is 2 zeros are here. It adds, it stabilizes the system, and also it adds phase angle to reduce the overshoot. This is the basic characteristics when we talk about PID controller in frequency domain. So that's the reason how we overshoot and things are controlled. Because of adding a phase, it reduces the overshoot. Let us see graphically how this is enhanced. Okay. So I would like to say here you have a K, right? I'm writing it tau 1 as plus 1, tau 2 as plus 1 divided by, I'm writing in general form. This diagram is I have taken from the Massachusetts Institute of Technology courseware. So K times tau 1 as plus 1, tau K as plus 1. This structure is coming from PID structure. So this is the combination. This is from actually PI, and this is coming from PD. And the combination I'm writing as K times tau 1 s plus 1, tau K s plus 1 by S. There are 2 zeros and 1 pole which is at the origin. Now we are going to plot the magnitude and phase actually. So you just take first K. K, you can draw some line here, right? This is my K here. Okay. So second one is what actually? Second one is, this is my dotted line. I'm talking about this dotted line, right? This dotted line I'm talking about, that is nothing but K. Some K I can be able to draw this. And second one is I'm plotting the integrator. What is the integrator? Integrator is minus 20 dB per decay. So I have drawn that 20 dB per decay line. And third one is tau 1 s plus 1. So till the first tau 1 s plus 1, till this point, this is my tau 1 here, right? This is my tau 1, first corner frequency. This is 0, so it takes up. So I like to draw here, it comes here, after tau 1, it takes up. 2 plus 20 dB per decay. Hope we can able to follow it. Then next one is another 0, again at corner frequency 2. So it means, so till the next corner frequency, it is 0 magnitude, and then it takes up. This is my tau T s plus 1. So I am able to follow tau 1 s plus 1, and this is tau T s plus 1, and this is my K, straight line is a K, and my S is like this. This is my S. That is minus 20 dB per decay. So if there is a 0 plus 20 dB per decay, it's slope, and if there is a pole, minus 20 dB per decay. Integrator and differentiator. If there is a pole of 0, it will, with respect to till the corner frequency is 0, and then beyond the corner frequency, the frequency takes up, and the magnitude plot becomes plus 20 dB per decay line. Right. This is what we are. So now we combine this. So what will happen now? Here it is 0, right? You have here 2 poles. 0 provides this, and you have a K, and here this provides this. So this gain all this magnitude multiplied, and we are starting like this, right? So this times. So what is the slope now? So zeros contribute 0 till corner frequency tau 1, but there is a pole which gives minus 20 dB per decay. So I'm starting from the starting magnitude is this. Then I start from here till my first corner frequency as minus 20 dB per decay. Okay, and then what will happen now after corner frequency, first corner frequency, this tau 1, right? Frequency, what will happen now? So it takes up plus 20 dB per decay. But already we have a integrator which is minus 20 dB per decay. So plus 20 dB per decay, this and this get cancelled. Till what frequency? Till the next corner frequency, tau 2, this frequency. So your magnitude becomes 0. Just I am keeping constant, not 0, I am keeping constant, because this slope is 0, right? Then later what will happen now? I have 3 slopes here. One is minus 20 dB per decay, that is integrator. And second one is 2 zeros. One is this blue line minus plus 20 dB per decay, and second one is minus plus 20 dB per decay. That is with respect to tau 2. So by adding this plus 20 minus 20, that resultant become plus 20 dB per decay. So my final slope will be this. So this is the original characteristics of the PID controller. Actually, magnitude characteristics of the PID controller. Same thing we can replicate actually for the magnitude plot, phase plot, because so far what you learned actually in your control theory is magnitude approximations, with 3 dB approximations we learned. But we can also do the same thing actually for phase approximations. If these details you study the not MIT poster, actually it is available actually. So just I'm taking from that. So phase also can be approximated, and we need not go with any exact phase plots. Likewise, we can K. It is independent of phase is independent of K, so it is 0, and there is a tau. So you have a response of tau here, and tau 1 is here, and tau 2 is here. So finally, integrator is minus 90 degree, right? So both the zeros, it reaches at plus 90 degree. That's what is shown here, and you can combine this plot. Finally, you get something like a response what is shown here like this. Only the corner frequency it breaks, remaining become a slope actually. This is something like a phase characteristics, we'd like to say approximated asymptotic phase characteristics of the PID structure. So far, what you learned is you people always learn the plant and how the plant can be used, how the plant characteristics can be seen from the Bode plot, magnitude phase plot, and step followed by stability analysis, etc. But here, I have taught you how that PID controller can be seen. Characteristics of the PID controller can be seen in the frequency domain. Okay, so this is what I expressed here. So you please go through that. Okay, whatever I explained, it is there. Okay, I will go to the example. So the 5 minutes just to complete it. We will take an example of something like a simple data dynamics is considered, like 1 by s times s plus 4 times s plus 6. It is decided to have designer controller. This is a problem I statement I had given such that the close to dynamics should meet peak overshoot is 10%, less than 10%, and setting time is less than 1.2 seconds. So we need to, you can use scissor tool by keeping in mind that what are properties of PID control structures. Okay. So just without controller. So normally we have a G and GC without G. No G is here. Only with G. I have drawn the open to Bode plot. That is what that we term as uncompensated Bode plot. So I would like to measure what is my gain crossover frequency. Okay, my gain crossover frequency is 4.9, and my gain margin is 47.6, and my phase margin is 89 degree, and the system is stable. My closed loop system is stable even without compensation also. But what I need now, I need to have a overshoot this and setting temperature. So I need to have a simulation, time domain simulation I would like to apply. So I applied a time domain simulation because this whatever I get actually in frequency domain here, right? So I applied a time domain simulation. Just I have checked whether I can able to meet the given specific gain less than overshoot. Yeah, well, there is no overshoot at all. But setting time given is 1.2 seconds. But here the setting time is something like 90 seconds. Okay, which is not desirable. So I can develop a PID controller, right? So I just am giving the brief introduction about what kind of controller I need to develop. So one has to first give the uncompensated magnitude plot. You have to shift the magnitude plot like this. So this is my magnitude plot. This magnitude plot should be shifted. It has to go upward. If go up means what actually? We need to increase the value of the K. That's what I am saying here. So for uncompensated magnitude plot, to increase the gain crossover frequency, right? So which in turn increase the close to bandwidth. So increase the close to bandwidth, what will happen? There is a inversely proportional effect, so it will reduce the rise time. So this is possibly by using the simple open loop gain. By increasing the open loop gain, the Bode plot getting shifted, magnitude plot getting shifted. But what will happen now? Due to mere increase in such a gain, right? So peak overshoot, because it reduces the rise time. Reducing rise time normally introduces peak overshoot, right? So what do you need to do now? I need to add 1 0. So then what kind of control do we need? I need to have a PV control. So you got it, no? So you got to see the open loop characteristics and time domain characteristics also you can see. And from the open loop characteristics, frequency characteristics, you would like to see what other things need to be improved. So I'm saying that first I can introduce the gain such that I can shift the magnitude part so that I can able to get the required bandwidth. But at the same time, it will reduce the increase in bandwidth actually reduce the rise time that introduces peak overshoot. So to reduce the peak overshoot further, I'm using a simple 0 such that with appropriate location to increase the phase margin. So this will reduce the overshoot, right? So and also increase the close to bandwidth, thereby meeting the given specifications. This is what normally we do actually for the design of controller. Finally, about the controller which I obtained actually based on the procedure is PI controller with parameter KP equal to 128.04 and my Ki is 0.5. Sorry, D control is 0.5. So after doing with this, I read on the simulation actually. So my magnitude plot is here. If you look at this, gain margin is infinity here. Frequency is also infinity, and it is a stable loop. And when you look at the phase margin, 57.4, and that frequency of 6.46. So this is what I have obtained actually from the body magnitude phase plot. But I want to look at that my specifications are met, so I need to draw a time domain characteristics. So the time domain characteristics, I can able to find that my specifications that is 1 point less than 1.2 and less than less than 10 percentage, less than 10 percentage. Okay. So these are the ways normally we do control system design. So we have to see what are the always I like to suggest you that you always draw open book characteristics and see that what are the characteristics need to be improved, and based on the requirement, one can able to develop whether PI control is required or PD control is required. So because every control parameter has its own characteristics. So how these characteristics can be enhanced in the frequency domain analysis, we have seen you. So you have to carefully do that such that one can able to get the required specification at some point. So this presentation is actually obtained written from based on the two books actually from Cover Digital Control and State Variables, and second one is chapter 8 Control System Engineering book. So these two books actually as a reference for developing this theory. So with this I would like to just stop my lecture. If you have any questions, I will take them.
So just one question in the chat box.
Yeah.
So shall I read out the question from the chat box?
Yes, please go ahead because I am not able to see it.
Yeah. The question is from Mr. Tirumurthy M, and it says, how do you guess 1 degree of freedom is enough for a percentage overshoot of 4.6?
So we mean talking about simple PI controller, right? I'm just going back to what was discussed. This is the controller which we talk about, right? So here we are saying that this is the question as asked: 1 degree of freedom controller, right? 1 degree of control means it can be a KP or can be a KI or can be a KD, and a KI and KD cannot be independently work. Only KP can work independently compared to other parameters. So definitely it works well because it's basically an analytical proof actually which we are showing here. So we are comparing the standard second order dynamics and we are finding what is making it. So my specification is given as overshoot, right? Overshoot is the only specification which is given, and that overshoot cannot be given directly; it can be given in the form of zeta. So once you know the value of zeta, I can able to compute KP such that I can able to meet. Yes, it is possible. It is done actually. It will be done like this way. I'm saying I'm stressing the point again. It can be done. That overshoot can be minimized with the help of simple proportional control itself. This is the evidence. Yeah.
So the next question is from Mr. Sandeep, and it says, can we use this method for an unstable system as well?
I'm sure it can be used for an unstable system also. Yes, I'm considering a simple case to make it to understand. So mostly we work on unstable process only. For example, magnetic levitation process or maybe a inverter pendulum process. These are all open to unstable process. So definitely one can able to develop a controller for such conditions using time domain analysis or frequency domain analysis. That's why I told whatever we are talking about is minimal polynomial and stable systems. There are other systems too. So non-minimal phase system is another category, and unstable systems are another category. These things, most of the practical systems comes with unstable systems, and sometimes non-minimal systems. So, but design of controllers for such conditions are a little complex compared to stable models, but still there are methods for doing that. These methods, out of a few methods, what I explained is also applicable for unstable models. Even some conditions, some methods can be useful for non-minimal phase models as well.
Yeah. So the next question is also from Mr. Tirumurthy, and it says, would you like to suggest some online resources to explore further into this topic?
Introduces?
To suggest some online resources to explore further into this topic.
No, you see, I am talking about textbook examples here, and I'm not talking about anything research in this. Actually, we have done a lot of work on that, but I'm not presenting it since it's a FDB program. I thought of giving you some kind of essence actually with respect to the basic. So it is you can all these materials can be seen actually from the basic control system textbooks. You need not go with any downloading papers. Yes, you want to go with some tuning methods, different types of tuning methods. Obviously, one you can explore through internet actually and see that how different methods are useful actually for the tuning of controls. That is available.
So the next question is from Mr. Varadarajan, and it says, how robustness of the PID design can be ensured? Is isodamping criterion alone sufficient for that?
No, it is not sufficient actually. I am sure about it is not sufficient. Yeah, just for demonstrative purpose, I'm using simple PID with a frequency domain specifications, which is one of the specification as robustness towards the gain actually, right? That isodynamic condition. Definitely, this alone not sufficient because in a real plant there are multiple parameters are varying, right? Not only one parameter. Okay. So if more than one parameter varies, definitely this simple 3 degree of freedom controller definitely will not meet the given specification. That's why people are going with the fractional controllers or higher order compensators, because we normally we look for this 3 degree of freedom controller or 5 degree of freedom controller like fraction PID controllers. But in NASA and ISRO and etc., they use higher order compensators. It is like a 10th order compensator or 15th order compensators normally they use for meeting such stringent conditions, including robustness conditions.
So the next question is from Mr. Ravishankar, and it says, does PID controller satisfy design criteria for nonlinear model? If yes, please elaborate.
I'm sure that controller can able to meet the given specification only at the equilibrium conditions, because if the equilibrium condition changes, because nonlinear systems have multiple equilibrium conditions, so it means multiple equilibrium conditions you need to develop multiple controllers, or the controller should be adaptive, either any one of this. So I'm sure that when the at the particular equilibrium condition, all these designs will work. So if the equilibrium condition changes, yes, we need to update the control parameter as well.
So the next question is from Dr. Harish, and it says, can you please elaborate on the damping coefficient zeta?
I'm not getting it. Can you repeat me then? Elaborate on?
Dr. Harish, what is the damping coefficient zeta, the definition for that?
Zeta you are talking about?
Yes, sir.
No, this is actually comes from this whatever we are talking about, the second order dynamics, right? This is comes from say for example, in case of second order dynamics, what will happen? So what is happening is I have not run like a standard second order characteristics here. So it will be like this, right? So what is happening now? I have a different characteristics with respect to zeta. Suppose if you say I have zeta is 0, what will happen? I can use root of s so that you can understand better actually instead of doing with time domain. Suppose if zeta is 0, what will happen now? So your denominator omega n square s square plus omega n square. So this component equal to component will be 0. So it means your poles are plus or minus j omega, right? So it means I have a pole which is lying on the imaginary axis, right? So it means when zeta is 0, what will happen now? The system is the poles are at the imaginary axis, that introduces sustained oscillations. It means instead of having a response as like this, I have a response which is oscillating. This is with respect to zeta equal to 0. So it's a sustained oscillation. It provides you the sustained oscillation. Suppose by increasing value of zeta, what will happen now? So there are two poles here. So two locuses. So one locus will move like this, and another locus will move like this, right? At some particular point, say for example, this variation actually we have measured that it's varying from 0 to 1. When zeta is varying from 0 to 1, poles move toward the left hand side, and it just is something like arc type. So when this goes beyond, right? When you say that zeta is at 1, both the poles are in the same place. Suppose if the zeta is greater than 1, what will happen now? One locus will move like this, towards left hand side, and another locus will move towards the right hand side. Okay, towards right hand side. So this is the root locus actually with respect to that. What it indicates now? So it indicates that when zeta is 0, it counts as sustained oscillation. So you are dividing into 4 characteristics for the given with respect to zeta. Zeta 0, zeta varying between 0 to 1, zeta equal to 1, and zeta is greater than 1. So that is undamped process, zeta equal to 0. And then second case is underdamped process, zeta is varying between 0 to 1. And critical process, critically damped process when zeta is equal to 1. And overdamped process when zeta is beyond 1. Right? So this is the way normally we classify, we characterize the given model. So accordingly, you will get the response. So one zeta 0, it oscillates like this. Zeta is varying between 0 to 1, it oscillates, then it settles. Zeta is 1, there is no overshoot, it goes like this and it settles. And zeta is greater than 1, normally that is first order dynamics kind of response, but it takes long time to settle. So it is basically sluggishness, introduces sluggishness due to the zeta variation zeta greater than 1. This is the basically affect the time domain characteristics with respect to different values of zeta. Yeah.
So the next question is from Shiv Kumar, and it says, if we have to do performance indices for multi-objective optimization, what can be the combination with performance indices?
Yeah, normally we see that. So normally we see in most of the time I do my research normally we do with the U square per C square. This is the one combination normally we do because U square that indicates that error and U square U indicates that your controller output. So we are trying to minimize both U, that is minimum energy control, and with minimum error. This is one way of looking at the problem, but it varies with case to case actually. Depending on the conditions, your performance index will vary actually. So one conditions which we normally simulate is U square, D square, etc. So if that condition may vary. Okay. So in case of suppose if some non-linearity is there, so what do you do now? Non-linearity comes into the picture. So my problem becomes minimum max and omega as well. So it becomes multi. So you need to minimum x and minimum. So you need to write the function such that it has to be minimize both magnitude and that oscillations and frequency in case of non-linearity, because non-linearity introduces some kind of limit cycle oscillation. So limit cycle magnitude will be x and that corresponding frequency is omega. So if you want to minimize or minimize this x and maximize omega, for example, or minimize x and minimize omega, so we need to have some kind of multi-objective functions. So these are the things which we come across, but it is basically with respect to the user defined problems. So any functions can be written, but it should be physically applicable actually, given model or given process. Yeah.
So the next question is from Ms. Richa Sharma, and it says, if rise time is high and overshoot is low, then what about system stability?
No, that's what I'm saying. When we talk about gain k, by increasing gain k, definitely it reduces the rise time. By reducing the rise time, it introduces overshoot. This is the basic problem actually, right, with respect to the proportional controller. That is why we are using a derivative controller. By introducing a derivative gain, this can be compensated. You have a maximum gain k at the same time by introducing the differentiator, so one can able to achieve the minimum overshoot. So we need to have a combination. That's what I'm saying. You cannot work parameters independently. So you need to have some kind of combinations such that you can able to get the design specifications.
Okay, so the next question is from Ms. Sarita, and it says, is PID controller applicable to multiple input systems?
Yeah, multiple input systems. We need to have yeah, it is. I'm sure it is applicable, but we need to if you have two input to output model. Definitely, we need to have two controllers. Single controller definitely cannot be cannot able to control both outputs, etc. So definitely, it requires two different two controllers in case of maybe in case of two input to output model. For example.
So the next question is from Mr. Abbas Kanungo. It says, FOPID is an advanced version of PID controller. Is there any application in which the response of PID is better as compared to FOPID controller?
So for see, this is a very complex question actually. The reason why I'm saying is we are always trying to prove some new controller with is better than the existing controller. Okay, so we always researchers always trying to prove that new controller like traction controllers are always superior than existing controllers. Okay, but my opinion about this is we can always work with a simple PID controller with certain fine tunings. So by fine tuning, definitely I'm sure that one can able to meet the specifications. But problem is if the number of specifications are more and the process is a little complex, we always prefer to go with the higher order compensators, something like fraction controllers and so on. So under this way, fraction order controllers are always superior and best actually. This is actually I'm speaking with respect to literature. My experience and with respect to industry people experience is they can use either simple PID controller or they can use a higher order compensator instead of some fractional controller or something like that. Because we can claim that the fractional controller will finally end up with a higher order compensator only, but the way which we obtained actually the higher order compensator from the optimization which we follow and follow for a conventional method and which we follow for the fractional methods are different. So I'm sure that the characteristics may be slightly changed actually with respect to different methods of tuning. I'm saying the resultant higher order controller from conventional method and the resultant higher order controller obtained from the fractional order controller, then 5 degree of controller. So it is my view, and it can be different actually for different people.
But I think there are no more questions.
Yeah. Okay.
Thank you. Thank you for this informative session, sir, and for taking time in clearing all of our doubts.
Yeah.
I'm
Okay.
sure almost all of us would have had a good insight into PID controllers.
Yeah.
On behalf of Electrical Engineering Department and Chemical Engineering Department and AICT, I express my sincere gratitude to Dr. Silvaganesan sir for accepting our invitation to be a part of this online faculty development program and spending his valuable time and efforts in educating all of the faculties, research scholars, and students from various colleges about tuning of PID controllers. Thank you, sir.
Yeah, I thank you once again for the organizer for the given opportunity, and I would like to thank the participant also listen and raise certain questions, which is valuable to me as well as to others. And hope any more questions, please kindly send an email to me so that I can able to answer it offline. Thank you very much. Thank you.
Thank you, sir. Sir, Kanakrishnan. Thank you, sir, for accepting our invitation. So we are requesting you to give more topic related to this tuning of PID controller. Because our MTech students, they do not know about this much in the basic PID controllers and how to tune that one, what is the application, how to implement for real time. So we are looking forward to hear from more related topics, sir, for forthcoming answer.
Thank you. Thank you, ma'am. Thank you very much. Thank you.
Thank you, sir. Thank you so much.
Bye.
I will send the mail.
Yeah, fine. Thank you. Bye. I will take a leave.
Thank you. Thank you, sir.
The feedback link has been posted on the chat box, and the next session will be starting by 11:30. So we request all the participants to please stay on the same meeting. Thank you.
Hello, Pavan sir. Good morning.
Hello, good morning.
Good morning,
Good
sir.
morning, sir. Pawan sir.
Good morning. I think my session will start at 11:30, right?
Yes, sir.
Yes,
Exactly.
sir.
Okay. So, shall I switch on my video also?
Sure,
Yes,
sir.
sir.
Okay. I understand that there is a recording of this lecture and it will be sent to TAL, right?
Yes, sir. We have to
Okay.
record all the session. We have to send the link and some video part. So we are requesting speaker to switch on the video.
Okay. So this recording video will be uploaded in YouTube also, right?
Not
No.
YouTube. I just uploaded it in the Google Drive. Then I will share with the Atal port.
Okay. Only to the group only. This group only they can download if they want,
Yes, yes,
right?
sir. Yes, sir. Yes.
Okay. So shall I share this presentation inside the WebEx or shall I share the video like desktop completely to show the PPT?
In the WebEx itself, share is available for everyone, sir. Share option is available for everyone.
Okay.
And now he start the welcome PPT, sir.
Okay. This is I think my session is first session today, right?
Second session 2 for day 3.
Oh, one session is already over from
Over.
9 to
Sir.
10:30, huh? Or 9:30 to
9:30 to
11.
11. Yes, sir.
11 o'clock. Okay.
Aswin, we can start. You can give the instruction.
Okay, ma'am.
It is now 11:22. Okay, 11:25 we can start. That is better.
Instruction. They will give some instruction, sir.
Okay. Right.
Then 11:30 you can start, sir. Now he will give instruction one.
Okay.
Good morning, everyone, and welcome to Faculty Development Program on Advanced Process Control, sponsored by AICTE Training and Learning Academy, organized by Department of Electrical Engineering and Department of Chemical Engineering, National Institute of Technology, Calicut. A few participants have joined now, and for them, I'll be reading out the guidelines once again for the smooth conduct of this session. By attending this FDP, you voluntarily agree to the terms and conditions set forth by the AICTE and the compliance of the academia or industry offering this lecture. No contents of this FDP may be copied, recorded, or reproduced in any manner without the written permission of the AICTE and the compliance of the academia or industry offering this lecture. Please mute your mic and turn off your camera at all times. Do not use the chat box for sending personal greetings. Use it only to post your doubts on the topic. Please do not click present now during the session. If you have any technical issues, make sure your internet connectivity is stable and then wait for 1 to 2 minutes. If the issue persists, use the WhatsApp group to address it. Our team will assist you. All participants must attend all the sessions and a test will be conducted at the end of FTP. Those who get a minimum of 60% of marks in the test and an attendance of above 80% will get the participant certificate. Once again, a warm good morning to all of you.
Shall we start the session?
Yeah, it is already 11:30.
Yes.
So I will start my session.
Sir, before that, we will give welcome and introduction.
Yeah, sure. Sure, thank you.
So I invite Danya ma'am to welcome sir.
So, good morning, sir. I am extremely delightful to invite you for our online FDP. So, the topic of Dr. Maladi today will be the steady state analysis of 2x2 control structure for FCC unit. So, let me first introduce Dr. Maladi. Professor Maladi is presently working as Assistant Professor in the Department of Chemical Engineering, NIT Calicut. Dr. Maladi has received his BTech degree from Osmania University, Hyderabad. He did his MTech and PhD from the Indian Institute of Technology, Kanpur. After that, he joined the Max Planck Institute for Dynamics of Complex Technical Systems, Germany, for postdoctoral fellowship. His career is decorated with several reputed awards and fundings. He is actively associated with different societies and academics. His research interests include design, modeling, simulation, and control of reactive distillation systems, process heat integration, nonlinear dynamics, and bifurcation of chemical process, adsorption, reactive and non-reactive systems. He has published more than 25 research papers in peer-reviewed international journals. His contributions have acclaimed recognition from honorable subject experts around the world. He is a lifetime member of Indian Institute of Chemical Engineers. On behalf of the online FDP term, I invite Professor Maladi and hand over the session to him. Welcome, sir.
Thank you very much, Dhanyaram, for the introduction. In today's lecture, I am going to talk about FCCU, that is Fluid Catalytic Cracking Unit, and I present you 2x2 regulatory control structures for FCCU, and I will present a comparison of the steady state performances of these control structures. So before going to that, I want to give you my reflections on our profession, that is teaching. So I have prepared 3 slides for that, and you please permit me to present this in next 10-15 minutes. So first of all, to be a good teacher, one must have good oral and written communication skills. So this is very important as a teacher. How we acquire these skills? By reading, by listening, and learning the writing skills from others. So we have to read books, we have to understand how they are presenting their ideas, and when we are presenting our ideas in front of students, we have to implement them. If we possess good oral and written communication skills, this will really help in making quality question papers and lecture notes, which will make us efficient teachers. These good oral and written communication skills are also very important when teachers are involved in the administration activities in the respective institutions, and these communication skills are also very important in the interpretation of the directions from the higher authorities. So to be an academic administrator, one must have good oral and written communication skills. So when we go to the class, we have to prepare the lessons with focus, and students are also look for teachers for effective delivery of the contents. So for this purpose, every teacher must must acquire new skills, and we have to observe other good teachers, and we have to adapt those skills. So since teaching is a lifelong learning experience, so it is very important that we emulate the skills of others. We have to have clarity in our thought, and we have to speak to students only if it is necessary. We have to encourage the students, and we have to supply the motivation, but we have to limit our communication as minimum as possible. We have to be very sincere. We have to look for betterment for ourselves and for others. We have to interact with students inside the class without hurrying through the lessons, and we have to give them best knowledge about the basics of the subject. And we have to adapt the new teaching aids for the effective delivery of the contents inside the classroom. So the teaching also now it is now ever changing. We have seen this recent COVID-19 here. Then we are not able to do the offline teaching. So we are now in this online teaching. So we have to adapt these ever changing dynamics of our profession. We have to stay focused, and we have to be a lifelong learners with passion. With my experience, I can tell you a good teacher can excel in all professions. If we have good oral and written communication skills, you can excel in any of the professions that you take. So this is the thing. And next I will tell you one quotation by J.R.D. Tata. This is a very, very important quotation which I liked it very much, and I want to share with you. You can read this. No institute of science and technology can guarantee discoveries or inventions, and we cannot plan or command a work of genius at will. This is an important observation from an eminent, he is an eminent industrialist, Tata, you know, J.R.D. Tata, and he was conferred Bharat Ratna Award in 1992. Now I will continue this, but do we give sufficient thought to the nurture of the young investigator, to providing the right atmosphere and conditions of work and full opportunity for development? It is these things that foster invention and discovery. So we are all teachers. We are working in various institutions. It is our duty to create the innovators, and we should not look for the innovation bias. If we can create a workforce which is going to contribute well in their future, then it is our success as our teachers. So the duty of teachers that I will tell you now I have shown one more picture here. This person is Venkataraman Ramakrishnan. He was conferred Nobel Prize. Once he gave a lecture in Indian Institute of Science. One student asked him a question that he wanted to get Nobel Prize, and the student want to know the procedure and how to get the Nobel Prize to Venkataraman Ramakrishnan, who is also a Nobel Prize winner. And Venkataraman Ramakrishnan replied that you will not get the Nobel Prize, please sit. That's it. So that is the answer. So you cannot command invention, discovery, awards, etc. by will. They will come automatically. If you are behind your work and profession. So duty of teacher is very, very important. So as we are working in various technological institutions, we have to create future innovators and leaders. We have to create qualified human resources for industry. We have to create persons of sincerity and integrity. We have to create professionals who can focus on innovation. So we have to create skilled workforce for this world, for this country, for this world. So for this purpose, we have to treat the students with kindness and gentleness. We have to set boundaries for self and others. We have to maintain the decorum of workplace. There is no retirement in teaching with an ambition for lifelong learning. So hope you have understood the quotation of J.R.D. Tata and you have understood the spirit of our teaching profession. Now I will go to the next slide. So these are some of the reflections which I don't want to go into now because we are already running out of time. So here we have to teach the basics correctly in the class. So we should not relax our seriousness. Okay, whatever seriousness that we show in the first class, it must continue till the last lecture. Generally, many of the teachers, what they do is last portions, okay, you can read it, you can read it. You should not do that. Till the last lecture, last minute, you have to show the seriousness in the class. Now I will take one more quotation from Albert Einstein. If you can't explain it simply, you don't understand it well enough. So you have to study well to explain the things in a simplistic manner. But at the same time, everything should be made simple as possible, but not simpler. So you have to maintain a balance. If you can explain a particular concept in 2-3 ways, that means you have understood it very well. So you have to focus, you have to prepare well before the lecture, and you have to show the seriousness from the first lecture to last lecture. Okay, this is my point. So now we will come to the topic. Now we will come to the objectives of chemical process control. In the case of chemical process control, first we see what are the objectives of chemical process control. First one is safety. Safety of the equipment, safety of the workforce, and safety as far as environment is concerned. So safety of the equipment, all the pressure, temperatures and other conditions, they should be within the allowable limit. That is the purpose of chemical process control. Second purpose is we have to maintain the quality of the product and the desired amount of the product. When we design a plant, we generally set some target. So that target we have to meet every day, every minute, every second. So quality of the product is also very, very important, because if there is no quality, then we may run at losses. Next point is environmental regulations. You see, nowadays, the concern about the environment is increasing. So similarly, the industry is also molding towards the ever-changing dynamics of environmental regulations. In olden days, we do not have any standards, but now we have Bharat standards 1, 2, 3, 4, 5, 6. Now we are running Bharat standards 6. So you know the environmental regulations, what happened in Delhi, they have banned the diesel buses. Now CNG buses are running. In the case of industry, if we are sending some effluent into the atmosphere, we have to treat the effluent in a way that it won't harm the environment as per the standards prescribed by the government agencies. And operating conditions also must be such that it won't affect the surrounding that surrounding environment of the factory. So these are the objectives of chemical process control. Next point is operating conditions. The process equipment, it should run within the limit that is prescribed by the design engineers. So specified limits are there, that limits these equipments should not cross. Next one is economics. So with respect to the market conditions, our main aim is, in the case of chemical process industry or any other industry, the main aim is maximization of profit and minimization of expenditure. So process control engineers play an important role in all these areas. So in short, The objectives of chemical process control are given below: suppressing the influence of external disturbances, ensuring the stability of chemical processes. So what is stability? I think many of you know very well what is stable and what is unstable. And optimization of the performance of a chemical process under the combination of the above. So these are the objectives of chemical process control in short. So when we are working in chemical process control, first we decide the objectives, then we design the control problem, then we offer the solution for the control problem, right? So these are the objectives. Any one of the objective also we take and we address that problem with our knowledge of control. So when we see a process, we consider the process with which we want to design a control strategy that is called a system or process system. So for the process system to devise control strategies, first we have to understand the process very well. We have to see what are the input variables and what are the output variables of the process and what are the potential disturbances. And in that, we have manipulated variables which can be manipulated. So these comes under input variables. All manipulated variables are input variables, but not all input variables are manipulated variables. So manipulated variables are subset of input variables and not vice versa. Similarly, controlled variables are subset of all output variables. In some of the input variables and some of the output variables, we will not be in a position to measure them. So we have measured variables and unmeasured variables. Then we have disturbances. So when we see a process, we have to list all the process variables, which are external disturbances, manipulated variables, unmeasured outputs and outputs. No, manipulated variables, outputs, unmeasured outputs, unmeasured disturbances, measured disturbances. Once we know all these things, then this is first stepping stone to understand or to design the control problem. Now we will understand what to control and what to manipulate. What is the relationship between these two? If it is a SISO system, single input, single output system, we will select one input and one output. Now we will see what is the relationship between this output and input. Is it linear? Is it non-linear? All those things. That knowledge is essential as far as the control is concerned. In the case of control, we have to understand all the subjects. Each control problem is unique. Each control problem is unique. Electrical engineering people are having different control problems, and chemical engineering people are having different type of control problems, because chemical systems differ from the electrical systems. Mechanical systems, they have different problem, right? But the tools that we use are same almost. So in this way, control engineering is something unique. So that is why many institutions are having control engineering as a special discipline. When we see the difference between modeling, simulation and control, in the case of modeling, we will be knowing the input and output, but we do not know what is the relationship between input and output. And sometimes it is possible to come up with the first principle modeling, where we will take material balance, energy balance in the chemical engineering systems, and we will come up with models, that is unsteady state models, those differential equations. So with those differential equations, we will be knowing the relationship between input and output. So if input is known and output is known, and we don't know the model, and we are given a task to develop a model, that is called modeling. So artificial neural networks, all those things come into picture there. If we are not able to come up with the first principle modeling, then we have to use the artificial neural networks, soft sensors, all those things, soft computing techniques. Sorry. So modeling. Next one is simulation. What is simulation? If input is known and model is known, and we don't know the output. So simply now you have the model which gives the relationship between input and output mathematically, and you do not know, you know the input but you don't know the output. Then you will write a code, okay, whatever model that is there, that you write a code in that language, okay, whatever the language that you know, then you come up with the output. You will calculate the output. That is called simulation. The third situation where we have model, we know output. We know output means we will set the target. This output I need. This is the model. And you want to calculate the input. This is called control. If you want your son to study for two hours and you know about your son very well, then you will do something like input you will give. Then you will achieve the target. Okay, what is the target? Your son must study 2 hours continuously. So input you will give, something you will do so that he can sit and study. So this is called control. So control is very easy subject. If you can understand the everyday affairs, then it is very easy to understand the subject of control. But to be a successful control engineer, you have to understand many subjects, basics of engineering, basics of science, many areas of mathematics you have to know to be a successful control engineer. So having understood the difference among these three, that is modeling, simulation and control, I will come to the control of a process. So in this slide, in one side I have shown one dot, in another side I have shown a line. Why I have shown this? In the case of dog, it is very easy to control. In the case of line, it is very difficult to control. I cannot go into the line sketch. Why I am not going inside? Because line behavior is unpredictable. Although it is very friendly to that person, you may not be knowing when it becomes violent and it will start biting him. We don't know. But in the case of dog, even though it is of the size of the lion also, okay, dog behavior you can easily predict as it obeys the dictums, but whereas a lion, it will not obey and it is highly unpredictable and its behavior is not known. Similarly, when we take processes, some processes are very easy to analyze. For the given input, you can predict the output by your experience. In the case of chemical processes, sometimes many of the chemical processes in industry, they run in manual mode. So man will be the engineer. So man, he knows very well what to do. Okay, this is input, this will be the output. Like that, he will apply his own logic and he will apply the controllers. He will manipulate the control valves in a way that process will not run out of control. But we have non-linear chemical processes now, non-linear. You cannot predict the behavior. So you cannot predict the behavior because of the lack of knowledge about the process. If you have sufficient knowledge about the key variables of the process, then you will be able to see the boundaries in which the process behavior is non-linear. So for this purpose, what you need? You need a model. That model must reflect the realistic conditions. When you give input to that model and you simulate it, then you should get the output. Then you have to tabulate, or you have to make a graph between the input variables and output variables. With respect to input variables, how these output variables are changing under steady state conditions. Okay, what is steady state conditions and steady state analysis, that we will see in the next slide. So if you want to understand, if you want to understand the control, first you have to understand the modeling and you have to understand the simulation. There are so many limitations as far as modeling is concerned. We make a lot of assumptions in modeling, which may lead to erroneous results as far as control is concerned. Okay. So first we have to understand the process very well. When we understand the process very well, then it is very easy to control, as if the behavior of patient is understood by the doctor. Our behavior are in the sense like, body, etc. How is health, all the data, everything. If he knows, then the doctor will sit and he will read everything. Oh, this is what happened. Okay, I think this is going to happen like that. See, doctor is also a control engineer. See, doctor is also a control engineer, but his machine is our human body. And control engineer, he will see the plant. So he will see, okay, this is going to happen, that is going to happen. Okay, you have to switch it on, switch it off. So in this way, control engineers also will work by sitting in the control room. So control is very easy if you understand the process very well. First of all, you have to understand the potential disturbances. You have to understand the input-output relationship. You have to understand the what-if scenarios. Then it is very easy for you to devise control strategies. Why we have to design the control strategies? We have to meet the objectives of the control that I have explained you in the first slides. So first of all, very good training is required, like the way we get trained before driving the vehicle on the highways. We will go to driving school. We will understand the system very well. Okay, why we are understanding the system very well? Because when we go to driving school, we will understand the nitty-gritties of driving. Then we will become driver. Similarly, if you want to control the process, first you have to understand the process very well. Then you will come to know about the non-linearity of the process or linearity of the process. Okay. Now we will come to the fluid catalytic cracking. So what is fluid catalytic cracking? What is this process? We will see first. Okay, what is this process? In olden days, in 1920s, when petrol was discovered, there was no demand for the light hydrocarbons. What is the meaning of light hydrocarbons? Whose molecular weight is less than C7, C8. C means carbon, C6, C7 like benzene, toluene, like naphtha, petrol. So the demand for this type of chemicals is very less. So in those days, people used to travel by ships. In the case of ships, they used to have high molecular weight gas oil, high molecular weight oil, which is very much like viscous. But as the technology, as the technology progressed, there was a demand for light hydrocarbons. So there was a demand for a process to convert high molecular weight hydrocarbons to low molecular weight products. So initially thermal cracking was developed. What is thermal cracking? Just you send this high molecular weight hydrocarbons into a reactor which is at a very high temperature. At very high temperature, this high molecular weight hydrocarbons, their chains will break and you get the light molecular weight products. So initially thermal cracking was practiced. Then over the time, they understood that they can use a catalyst and they can reduce the temperature of cracking. And over the time, many catalysts were developed, and the fluid catalytic cracking unit also, from batch to continuous mode, it was changed. Why it is changed from batch to continuous? Because of the demand. Because of the demand. In some places, in some places in India, 24 hours they supply food, roti. Now they have continuous process. Just you pour the atta and water, then at the end you will get the chapati. So that is a continuous process. Why they have invented that? Because of the demand. You need maybe 20 lakh puri per month. 20 lakh puri, if we sit and do it, it is very tough. So what they did, they have invented a continuous process. Similarly, as the demand increased, now thermal cracking is replaced with catalytic cracking. And catalytic cracking also, there are several designs. Now, this type of unit where you have R by R, that is regenerator and reactor. This design, that schematic that is shown here, this design is being vividly used now across the world in many refineries for the conversion of high molecular weight hydrocarbons to light components. So in this photo, I am showing one FCC unit from an industry. This is the photograph. You can see this is very tall unit. In Kochi, we have BPCL refinery. There also we have this type of unit, BPCL Kochi. In the case of Indian Oil Corporation refineries, you will find this type of units. Only one will be there. Only one unit per refinery. If demand is there, you can have one more refinery. But generally demand won't be like that. You will have only one facility. You will have one refinery. And in the case of refinery, this FCC is now regarded as workhorse. So many of the chemicals that are coming out of FCC unit are giving a lot of profits to the refineries. Okay, now we will see what is happening in the refinery and how it is designed. That we will see in the next slide. But in this slide, I will tell one point. In the case of chemical processes, what is most important? The important thing is mass balance and energy balance. For the analysis of chemical processes, first we have to consider mass balance. Second one is energy balance. When we understand mass balance and energy balance very well, see, control is all nothing but balancing. That's it. Mass balance and energy balance. Whenever mass accumulation is there, it will lead to failure. Whenever energy accumulation is there, temperature will go up. Then you can't control. So you have to understand mass balance and energy balance. If mass balance and energy balance are satisfied, then you are achieving a very good control. So underlying principle of control is nothing but mass balance and energy balance in the case of chemical engineering processes. Maybe in the case of electrical engineering, it is nothing but like charge balance. In the case of civil engineering, force balance. Mechanical engineering, force balance. So for control point of view, delicate balance of mass and energy flow is very important in understanding the control of fluid catalytic cracking unit. So before going to control, we have to understand the variables. What are the variables and what are the key variables? Now, in this slide, I am showing you a diagram of fluid catalytic cracking unit. I hope everyone is able to see this. In the case of catalytic cracking unit, in the bottom there is one arrow. From this arrow, raw oil that is heavy, that is pumped into the riser. In the riser, this is a pipe. This is a vertical pipe. So in this pipe, the feed oil will mix with the catalyst. So catalyst is nothing but in this case, in the case of refineries, zeolite catalyst is being used. See, catalyst is nothing but like a powder type, a powdery substance. So this oil and that powder, these two are mixed, and in this riser, the residence time for oil is only 0.1 seconds. Very less amount of time, very high temperature. So from the riser, it will go into the reactor section. So whatever the catalyst that is utilized, that is being utilized for the reaction, that will again it will come to the regenerator. In the case of regenerator, the activity of the catalyst is being retained. In the case of cracking reaction, what happens is the high molecular weight components will become low molecular weight components. Along with low molecular weight components, some carbon will be formed on the surface of the catalyst particles. What is carbon? C. Okay. What is low molecular weight components? Maybe C5, C6. So some cracking will happen as far as low molecular weight components are concerned, and it will end up in the form of coke. That is nothing but the carbon, C. So that will deactivate the catalyst. So you cannot reuse the catalyst. To reuse the catalyst, we have to remove the coke that is formed on the surface of the catalyst. For that purpose, we have a regenerator. In the case of regenerator, we send air which is at very high temperature. This air which is at very high temperature, it will react with coke, and the coke will be converted to carbon monoxide and carbon dioxide. This reaction is highly exothermic reaction. Exothermic reaction means heat will be released. It is very high exothermic reaction. Two reactions are there. C will become CO, that is carbon monoxide. CO will become CO2, and sometimes C will be directly converted to CO2 depending upon the conditions. So the purpose of the regenerator is to bring again the activity of the catalyst back to the original state. So regenerator is there. So this is reactor. So this catalyst will circulate here. Okay, first it will come here, it will react. Then after that, the spent catalyst is sent to regenerator. Then again, this air will be blown into the regenerator. Then carbon dioxide, carbon monoxide will form. They go out of the refinery as flue gases. So from these flue gases also we can recover some energy. So this catalyst, which is at very high temperature because of the exothermic reaction, no external heat supply is required. This raw oil which is coming inside, that will get heated up by the contact of the regenerated catalyst, which is at a very high temperature. So both will go up in this riser. Then again the cracking reaction will happen inside the riser. Now, once this oil is converted to lighter products, this will go into the reaction section where some of the catalyst, which is in the form of particles, that will be separated. So catalyst will be stripped by the action of steam. Then these lighter products will go to a distillation unit. There you will get unconverted heavy gas oil, light gas oil, gasoline, and lighter components. So these are the products. Now, from the fractionation unit, some slurry settler will be there. So there you can retain the catalyst again, that catalyst, and some of the heavy gas oil that will go into the feed here. So we can change the catalyst for every 2-3 years. Sometimes 6 months, 7 months time it will take. So they will change the catalyst. So every 6 months you will see that new catalyst is used. So this is a very big industry, the preparation of catalyst. And these companies, they won't tell you the trade secret, which catalyst they are using. So very big companies are there like Shell, Reliance. So these companies, they don't tell you about the technical details of the catalyst, because that is a trade secret, and like millions and billions of rupees of money is involved. So this is the fundamental operation of the fluid catalytic cracking. There are so many separation processes are there, like we have to separate solid and gas. In the case of reactor, we have to separate solid and liquid, and here we have to send the spent catalyst here. Here again, in the case of regenerator, we have to separate this flue gas from the solid catalyst, right? So whatever the operation that is happening in reactor and regenerator, it is very vigorous. So you have to use many separation units to separate solid and gas, liquid and gas. But essentially, there is a catalyst which is circulating like blood. So spent catalyst is coming here. Then again, regenerated catalyst is going here. So here, what you can see, okay, one point that is very good point. Whatever the oil that you are sending here, its weight must balance with respect to the carbon. So see here we can see like carbon balance. Carbon balance means whatever the carbon atoms that are coming through the raw oil, they are found in the flue gas. Hello? And they are found here. Hello? Any doubt is there?
Okay. No problem. Leave it.
Okay.
No problem. Leave it. Anyway, the document you have the submitted. Yeah, no problem. Then leave it.
Hello?
So we request the participants to please mute their mic.
Okay. Okay, now in this FCC unit, there is circulation of mass and circulation of energy also. So energy that is generated in the case of regenerator is going to the riser and reactor sections, and mass, there is a mass balance also, that is the catalyst that is coming from the spent catalyst side should be equal to the regenerated catalyst. If it is not there, then we have to add the makeup catalyst time to time. So this is a continuous process. This is a continuous process. So catalyst will be circulating, you are sending oil, then you are getting flue gases out, and you have a fractionator unit. You are getting gasoline, light gas oil, heavy gas oil, everything like a continuous. Okay. Okay. Now, in the case of reactor, we have to understand the cracking reactions. First, we have to understand the cracking reactions. So, cracking reactions are not like simple enough to understand. Now, in literature, they have proposed lumped kinetic models. In the case of petroleum, do you know the formula of petroleum? You don't know, because petroleum is a mixture of several hydrocarbons. There is no formula for kerosene, like no standard formula is not there. There is no standard formula. Similarly, heavy gas oil, there is no formula. Only they will see in terms of the boiling point difference. In terms of boiling point difference. So that is why lumped models were developed. So in this slide, I am showing you 7 lump model. In this lump model, you can see vacuum residue, that is lump 1, vacuum gas oil, that is lump 2, light FO, LFO, LPG, coke, dry gas, and gasoline. You can see, and you can see the reaction, that is cracking and its kinetic parameters, K14, K24, K34. So here vacuum residue is directly converted to LPG. This is the associated kinetic parameter in the case of reaction. So we have 4 lump model, we have 5 lump model, we have 7 lump model. Now we have 21 lump model. 21 lump model is there. So 21 lumps are being taken. So we have now 21 lump model that is being developed recently, and they will see the agreement between the simulation values and the experimental values, and they will see the agreement. Then after that, they will finalize which model we have to take. So 21 lump model now it is being used. Hello. So it is more accurate compared to the 5 lump model. What is the problem? Already the UAV only given the title. The title is Saravan Kumar Gurusamy, please mute your mic, sir. Saravana Kumar Gurusamy, Dr. Saravana Kumar Gurusamy, kindly mute your mic. Okay. Now we will come to the steady state analysis. Hello?
I muted.
Okay. Now we will come to the steady state analysis. See, FCC itself is a very, very complex unit. So in the case of FCC, many researchers attempted to do the steady state simulation and dynamic simulation using the models. In that model, they have to use lump models. So they will see the experimental values, they will see the predicted values from the simulation, and they will say that there is a close match between the experimental values and the simulated values. Then they will say that this model is very useful, you please use it. But every refinery is unique, because feed also will change with respect to the petroleum well from where you are getting the feed. Some feeds, they contain impurities in the form of sulfur. So there are so many complexities involved as far as the dynamic simulation and steady state simulation of FCC unit is concerned. Okay, now that is one thing. So whatever the complexity that is there, as academicians, we have to simplify and we have to give some predictions. We have to give some kind of we have to give some conclusions regarding the operability of the FCC unit and its control strategy. That is what we have done here in NIT Calicut. Now, steady state analysis. Steady state analysis is nothing but the study of the input-output relationships. Study of the input-output relationships. A control structure performance can be analyzed under steady state conditions. But dynamic simulations are necessary to validate the steady state analysis results. In earlier days, design and control, they were taken separately. Design first they will do, then after that they will try to devise control strategies. But nowadays, as the complexity of the chemical processes increased because of the challenges as far as environmental regulations are concerned, we want to invest less amount of money, we want to maximize the product, then we are combining two, three functionalities in one single unit. In earlier days, we have computers. In those computers, we use it to type. But after that, what happened? Their space increased. Then after that, we are able to watch movies. We are able to do many things using the computers. So many functionalities are there now. In the case of laptop, now tablets are there. You can see. So similarly, chemical processes also, there is a very big development. They are combining the functionalities of many unit operations. So the complexity is increased. As the complexity increased, control became difficult because of the non-linearity that is resulted from the complexity of the processes. That is very much evident. So that is why nowadays the control is also addressed at the design stage itself. So as the non-linearity makes the control more complex, steady state analysis is an effective tool to understand the control challenges. So steady state analysis became an effective tool, and there are so many papers on steady state analysis. So it is a very good tool to understand the non-linearity of the process and derive conclusions for the control. But we have to do dynamic simulations to understand the workability of the control structure that is suggested by the steady state analysis. See, steady state analysis will tell, when we see the Hero Honda, when we see Royal Enfield vehicle, we will say, oh, Royal Enfield vehicle, it can go to Delhi. So that is only a prediction, like steady state analysis. Okay, Hero Honda cannot go, right? But we have to take the vehicle to Delhi, right? Then only we can do that. So similarly, dynamic simulations we have to do to prove the suggestions given by the steady state analysis. Now, in the case of FCC unit, we have used CAT Cracker module in HYSYS. HYSYS is a commercial software for the simulation of chemical engineering systems. So in fact, process engineering systems. So in that HYSYS module, cat cracker module is there in the case of HYSYS software that we have used for the simulation of FCC unit. So this is a pictorial diagram of that HYSYS cat cracker module. This is screenshot. Now, for the steady state simulation, we have selected the components, we have selected the fluid package, we have selected the feed assay. So we enter into the simulation environment and we will set up a steady state case. Two types of combustion, as I told you, that is possible. One is partial combustion mode, another one is complete combustion mode. In the case of partial combustion mode, you have carbon monoxide. So carbon monoxide can be further reacted to CO2 when we have CO2, that is complete combustion. Complete combustion mode, you do not have CO. Everything will be burned into CO2. In the case of regenerator, all the carbon that is burned, that is converted to CO2. So that coke that is there on the catalyst, if it is burned, it is converted to CO2. That is called complete combustion. Two types of modes are there for the combustion. So we have selected the package. So these are the components of the reactions. Then we have selected we have to select a fluid package. So we have used Peng-Robinson equation of state. What it will do in the simulation, density, molar volume, pressure, temperature, all these things, they are all depend on the package that we take. So Peng-Robinson equation of state is an advanced equation of state that we have selected. So this is very much useful in handling all types of hydrocarbons, water, air, and all the typical components that are there in the case of FCC unit. Now, these are the control structures. See, entire FCC unit, you might have seen that the temperature of the regenerator and temperature of the cyclone. What is cyclone? In the case of cyclone, you separate the flue gases from the solid catalyst. In the case of regenerator, that is called cyclone. So that is called cyclone separator. Cyclone separator temperature, regenerator temperature, and reactor temperature. These three are the important output variables. Okay. Why these are taken important output variables? Temperature is very easy to measure. But whereas composition, it will take some time because of the lags associated with the equipments that are used for the estimation of composition experimentally. Now, what are the potential input variables? Input variables are the catalyst circulation rate. You have seen catalyst is being circulated from regenerator to reactor. Again, reactor to regenerator, regenerator to reactor, like that it is circulating. Right? So catalyst circulation rate is an important input variable. Next input variable is airflow rate to the regenerator. This is also an important input variable. So two input variables are being selected, and the temperatures of regenerator, temperature of reactor, temperature of the cyclone, these three are selected as the output variables, important output variables. This selection is done in 1993. In one of the papers, we have seen that these are the important variables, and the temperature is very easy to measure, right? So we have to select the controlled variables in such a way that they are easily measurable, practically relevant. Now, 5 control structures that are listed here. First control structure is conventional control structure. These names are given with respect to the pairing of the manipulated variables and controlled variables. In the case of conventional control structure, the catalyst circulation rate is used to control the reactor temperature, and the inlet airflow rate to the regenerator is used to control delta TRG. Delta TRG is nothing but regenerator flue gas temperature minus dense bed temperature difference. So that is called delta TRG. TCY. In the case of next control structure, that is Kurihara control structure, same input variables FC and FA, but FC is used to control the temperature of the regenerator and FA is used to control the regenerator flue gas temperature minus dense bed temperature. That the difference, delta TRG. So this is Kurihara control structure. Next control structure is alternative Kurihara control structure. You can see now what are the output variables and how the pairing is done. Next control structure is Higgs control structure. You can see here FC is directly connected to TR. So TR is the controlled variable and corresponding manipulated variable is FC. TCY, that is cyclone temperature, that is in the regenerator, cyclone temperature is connected to FA. So these are the pairings. Now, in the final control structure, riser regenerator control structure, FC and FA are paired with TR, TRG respectively. So these are the pairings. So it is a 2x2 control structure. So there will be interaction, right? Interaction will be there, but we don't know what type of interaction. If interaction we know, we will design the E couplers, okay, all those things. But you know, you have to make the control structure as simple as possible so that a person who is not having any knowledge about the control also should be able to understand the workings of the plant. You have to make as maximum as possible. You have to make the control structure very simple. That should be the aim. Next one is complete combustion mode. These 3 control structures are there. One is conventional control structure, Kurihara control structure, and riser regenerator control structure. But here you can see oxygen concentration is also a controlled variable here. Oxygen concentration in the flue gas. Oxygen mole fraction here in the flue gas. So in the case of partial combustion mode, 5 control structures are there. In the case of complete combustion mode, 3 control structures are there. These control structures are there in the literature. They are in practice from 1920s. But since we did not have proper process engineering packages up to 1993, only the knowledge that we obtained from the principle, from the workings of the plant. People used to have analytical, maybe they used to document the behavior of the process and they used to come up with solutions by experience. But now we have process engineering packages. We can predict the behavior with appropriate packages, appropriate models, since we have computers of very high efficiency. And there are so many advances as far as mathematics is concerned. for the solution of partial differential equations, numerical methods. So the subject developed. Those things we can use for the simulation of chemical engineering plants. So you have understood the manipulated variables, you have understood control variables for the two modes of operation in the case of FCC unit. So three control structures are there in the case of partial combustion mode, and in the case of partial combustion mode, 5 control structures are there. In the case of complete combustion mode, we have 3 control structures. So these are the base case values. These are the base case values like feed flow rate, feed temperature, feed pressure, specific gravity of the feed, then steam flow rate. In the case of complete combustion mode and in the case of partial combustion mode, CC represents complete combustion mode and PC represents partial combustion mode. So these are the hardware parameters and process parameters. The mole fractions of CO, CO2 and oxygen, everything is given as far as flue gas is concerned. Here you can see the reactor temperature, reactor pressure, TR, TRG, delta T, TRG, all those things are given here. TCY, that is cyclone temperature, everything is given there for the steady state conditions. For the steady state conditions, these values are taken from a journal paper that is published in 2001 in Chemical Engineering Science. This is from Korea. This paper research was done in Korea. So it was published in Chemical Engineering Science, 56th volume, 1973 page number. This is in 2001. It was published in 2001. So these parameters are taken from this paper, and we have simulated this in Aspen HYSYS CAD Cracker module. So I have shown you already how to select the package and what package that we have selected and what are the specifications and what are the components that we have given, that I have already shown it to you. Now we will see the performance comparison of the 5 control structures under partial combustion mode. So first we have taken 3 control structures: Higgs, riser regenerator and conventional. As I told you in the beginning, in the case of chemical processes, when we change the specifications, when we change the flow rates, our purity should not change. Our purity should not change. The purity of the product. But in the case of FCCU, what are the products? We have naphtha yield, we have bottoms, we have coke, we have LCO, we have lightens. So how they are changing with respect to the flow rate of the feed, because feed is an input variable. These are all nothing but steady state results, input output relations. What is input here? Input is FF and output is all these variables given in the y-axis. Okay, now you can see in the case of conventional control structure, in these 3 control structures, PR is controlled by the catalyst flow rate. So catalyst flow rate is changing. See here you can see with respect to FF, the catalyst flow rate is also increasing. If it is increasing, this is also increasing. If it is decreasing, that is also decreasing. And here we have the operating point 193.5 here. So you can see the control structure which gives minimum variation with respect to the products. That is the best one. That is the best one. Minimum variation in the yield of the products. So which one is giving minimum variation? So we have to analyze, okay, what is our objective and how the things are changing with respect to the manipulated variable. So from this we can conclude, okay, which one is better and which is working well as far as steady state is concerned. Right. So here we can see which one is better. Here we can see that in the case of naphtha, see, naphtha is an important product in the case of FCC. If you see the naphtha variation, you can see naphtha, whatever the design value, that is around 40.2, that is being maintained throughout when we change the flow rate of the feed. That is being maintained, you can see here. But other control structures, you can see there is a variation. So it is going here to 39.8, and in this side it is going to 40.8. So what are the control variable in the case of conventional control structure? TR, see, you can see here in the case of TR and delta TRG. Delta TRG. You can see here, these two are maintained. TR is common to all control structures. It is controlled by FC. You can see. But here TRG is the next control variable, which is controlled by FA. So in the case of Higgs control structure, TCY is the control variable. This is maintained here. So under steady state conditions, we have done the steady state simulations to understand the performance of these three control structures. When TR and TCY, if they are maintained at their steady state values, that is nothing but control. Right? So Higgs control structure, this is for Higgs control structure, TR, TCY. In the case of riser regenerator control structure, TR and TRG. You can see here, TRG is maintained at its steady state value with respect to the changes in FF. So we have done the simulations as if the control structure is on. So this steady state analysis has yielded one result, that is the conventional control structure is better to see less variation in the case of naphtha yield. You may say, sir, 40.4 to 40.8, very small difference. But it is a very big difference because we are handling thousands of tons of naphtha per year. So any small number change here will affect the production there. Right? So this is a very good prediction. Okay, we will come to the next slide. Here I have given a tabulated column. For the comparison, you can see there is minimum variation as far as naphtha is concerned. It is from 40.44 to 40.16. But in other cases, it is little bit more. That variation is more. So whatever result that I have shown in the graphs, I have given it in the table here. That's it. That is the difference. There is no difference. Now we will come to the two other control structures, that is Kurihara control structure and alternative Kurihara control structure. In the case of Kurihara control structure and alternative Kurihara control structure, you can see there is a little bit like multiplicity is there. Multiplicity means for a single output variable with respect to oxygen. You can see for 1.95 mole fraction of oxygen, you have two different feed flow rates. So this is called input multiplicity. Input multiplicity means for a single output variable value, you have more than one input variable value. Other type of multiplicity is output multiplicity. Output multiplicity means for a single input value, you will have more than one output value. That is called output multiplicity. But here you have input multiplicity. In the case of naphtha yield also, you have input multiplicity here. There is input multiplicity here. So this is the design state. So if you increase FF, if you decrease FF, in both ways, you will see there is a loss of yield. So these two control structures are not good from the steady state analysis results. From the steady state analysis results, this is the prediction. But we have to do the dynamic simulations to see practically whether these predictions are correct or not. But steady state analysis is a very good tool. And sometimes some control structures won't work. We don't know the reason. But when we do steady state analysis, we will understand why that particular control structure is not working. See, sometimes what happens is we seek infeasible set points. Infeasible set points. What is infeasible set point? If you go to exam is for for 100 marks. So you can get maximum 100. If you ask for 101 out of 100, that is not possible. So similarly, in the case of infeasible set points, control structures won't work. Control structures will definitely fail, and whatever the valves that are there, they will go to the saturation.
Will be joining back. Please stay on the meeting.
There is some problem in the network. Now I will share the content, please.
Yes, sir.
Okay. So this is control structure and alternative Hara control structure, and these are steady state relation results, study analysis results of the control structures. audio is not clear, maybe due to the fact that I have connected with my mobile network. Maybe that is the reason, because there is some problem with respect to the Wi-Fi institute Wi-Fi. May I try institute network now? Here with me, 10 minutes time is there. I have explained you everything. Now only the comments are there. Okay. Okay. So alternative Kurihara structure and Kurihara structure, they have certain problems. What are those problems? Multiplicity and naphtha yield is also decreasing in both ways. So in the steady state, we are getting maximum naphtha yield, but when we decrease the feed flow rate, when we increase the feed flow rate, there is a decrease in the naphtha yield. Why we are studying this? Because feed flow rate initial disturbance. Feed flow rate can change depending upon the demand. Understood now is Kurihara control structure and alternative Kurihara control structure. Not that much efficient, but conventional Hicks and other control structure, conventional Hicks and riser regenerator control structure, where temperatures are the variables. See, here also temperatures are the variables, but those three control structures are efficient. Now another potential disturbance that can come is the feed temperature. So these are the performances of the control structures. So as I explained you earlier, you can see the performance of the control structures with respect to the feed temperature variation. The feed temperature is around 520, 535 something, and it is varied between the figure. You can see how catalyst flow rate is changing under steady state conditions, and how this air flow rate is also changing with respect to the temperature of the feed. Okay, so for the three control structures, it is shown here. Okay. Now, if air blower discharge temperature is again varied, that is also a potential disturbance. So under steady state conditions, we have simulated the FCC unit for these disturbances for 5 control structures. So for the 3 control structures, because we have eliminated Kurihara and alternative Kurihara control structure because they are efficient as far as feed flow rate variation is concerned. So we did not study them further. Now we will come to the complete combustion mode. In the case of combustion mode, 2 control structures, conventional control riser regenerator control structure, you can see in the case of conventional control structure and riser regenerator control structure, you can see the performance of the 2 control structures under steady state conditions. Their performance is satisfactory. Only the naphtha yield is changing from like 40 to 39. Both control structures are almost, they are exhibiting similar type of performance. Right. Here you can see in the case of conventional control structure, the concentration of the oxygen in the flue gases is being controlled. See, here you can see this is constant. So that is being controlled. In the case of riser regenerator control structure, TR and TG. TR is here, TG, TRG. See, here you can see these 2 are the controlled. They are maintained at their steady state values, that is base case values. Now other variables are changing, both input and output variables. So these are the output variables. This is also output variable, but by controlling this, how those output variables are changing. Naphtha yield. We are inferring the temperature. This is called inferential control scheme, where we are naphtha yield. We are interested in naphtha yield, but we can't control naphtha yield because it is very difficult to control naphtha yield. You can control only the temperature. Temperature is being controlled. We will see how naphtha yield is being varied. Okay. Come to the Kurihara structure. This is Kurihara control structure. See, in the case of Kurihara control structure, what happened is we could simulate the column up to this is the design steady state. Okay, 195. We could simulate the column only in the direction of decreasing the feed flow rate. We could not simulate the column for the increase of the feed flow rate above the design steady state. We could not simulate. Then we have seen why it is so. Because when we increased the feed flow rate to 202.55 meter cube per hour, what happened is 987.9 Kelvin is the regenerator temperature at the design steady state. Okay. We could not achieve 987.9 degrees Kelvin in the regenerator with respect to the catalyst flow rate variation. We could not reach this. It is going like this under steady state conditions. If we seek this set point, dynamic simulations, what is going to happen? See, FC cannot see under dynamics the failure of this control structure you can see, because you are seeking infeasible set point value when you take the feed flow rate to 202.5 meter cube per hour. Our base case is 192 something, so 192.5. If you seek this, then you will not reach the regenerator temperature that is set at the base. Decrease set point value, maybe you can decrease the set point value to 987.4. So that may come to the steady state, but other things may get other things like naphtha yield, etc. They may get decreased, and your plant will be on the verge of a very big failure. So these things you can easily understand it, right? So I hope so these are the Netherlinsky index value and the relative gain array values of the control structures. In the case of Netherlinsky index, if the value is negative, so definitely there will be negative interaction. If it is positive, then the interaction is positive, but it has to be checked in the dynamic simulations. So for all control structures, we have taken the steady state gain matrix Ni and relative gain array. So these are the conclusions. We have taken closed loop steady state performances of 2x2 regulatory control structures for side by side FCC unit under 2 operation modes. 3 types of disturbances are selected. In the control structures where the catalyst flow rate is used to control the temperature of the reactor, we got favorable closed loop steady state performance. Successful regulation of conversion is seen as the key for the preservation of the product yields. Best workable control structures are identified for both operation modes. For these 2 modes, in the control structures where is controlled by catalyst flow rate, they suffered from closed loop steady state multiplicity, infeasible set points, and unfavorable closed loop steady state performance. So, thank NIT Calcutta for giving me this opportunity to speak in front of you. I thank Anish Thomas, who is my PhD scholar, and this is PhD work, and AICTE Academy for training and learning Atal for their sponsorship, and I also thank organizers Kanagalakshmi and Dhanyaram, and I also appreciate you for your patience and time, and thank you all for your attention. and my talk is over. If you have any doubts, then I can answer those questions.
Participants, you can post our questions and or you can unmute and you can ask questions.
Sir, so there are a few questions in the chat box. Shall I read them out? The first question is from Mr. Manitija, and it is, why can we not have flow rate of oil as manipulated variable to control regenerator temperature?
We can have that also, but we have to test it. See, these concepts are given in the literature. We have taken them directly. See, as you said, we can take the that, but that type of pairing is not favorable because we have to, as our regulation handle, we have to have the flow rate of oil in our regulate the production of the plant. That is why that choice is not good. That is why these 5 structures. Yes. Okay, next question.
So the next question is, it is from Mr. Gopinath, and it says, for liquid, mass and energy is taken for balancing. What to take for natural gas for processing balance?
Liquids. No, in the case of natural gas also, you can take mass balance. Yes, in the case of liquids, there is no change there. See, again, when you go to natural gas processing, pressure will become an important variable. So thermodynamic variables will come in. So you should have very good command over thermodynamics to know the energy balances. In the case of natural gas processing, I am not expert in natural gas processing, but I hope whatever the things that I told you will help you to understand the natural gas processing mass and energy balances. Because natural gas is a compressible fluid. Hope you have understood this. Any other question?
Sir, I think there are no more doubts, sir.
Okay, if you want to interact with me, you can interact with me. You can send a mail also. I am very happy to address any type of question that you have. I think some of the questions, I have seen one question. I think it is a bit complicated, and that person who has asked about the quality of teachers to be silent in front of the students, that I will answer him directly if he send me a mail or over the phone. So my number is with them also. If you want, you can talk to me directly. Okay, now my session is over, madam. Thank you very much.
Thank you for this insightful session, sir, and also for taking time and clearing our doubts. On behalf of the Department of Electrical Engineering, Chemical Engineering, and AICTE, I express our sincere gratitude to Dr. M.V. Pawan Kumar, sir, for accepting our invitation to be a part of this online FDP and spending his valuable time and efforts in educating the faculties, research scholars, and students from various colleges about steady state analysis of 2x2 control structure for FCCU. Thank you, sir.
Okay, thank you very much.
Thank you
very much.
Thank you so much, Dr. Pawan, for accepting our invitation and delivering a very, very nice talk. Thank you.
May I leave, madam?
Yes, sir. Section is over, sir. Okay. Okay.
Thank you.
Okay, madam. Thank you very much. And I am leaving, and I wish you all the best to all participants. Bye.
Thank you. Thank you.
The feedback link has been posted in the chat box.